Hello and welcome to Space Historians. I am truly glad you have joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our little blue world. Tonight, we are not racing through the stars. We are gliding gently, letting the silence of space wrap around us like a soft blanket. This is your moment to leave behind the noise of the day and step quietly into the vast, starlit corridors of cosmic history. Before we begin, I would love to know, where in the world are you listening from, and what time is it where you are? It always amazes me how, while the night sky may look different across the globe, the stars above have watched over every civilization in history. If you enjoy these quiet journeys through time and space, a like and a subscribe help keep this channel orbiting steadily. And for those who have already joined this growing constellation of listeners, thank you. You are part of this voyage, part of this shared wonder. Each episode here is not just about stars, planets, or galaxies. It is about the stories they hold, the myths whispered by ancient astronomers, the discoveries that changed how we see the universe, and the quiet mysteries still waiting to be revealed. Tonight, we venture into something that should not exist. A place so impossibly empty that when it was first discovered, scientists thought their instruments had failed. A region of space so vast that if our galaxy sat in its center, we might never have discovered that other galaxies existed at all. We are going to explore what hides inside the Bootes void, a hole in the universe 330 million light-years across, where 10,000 galaxies should shine, but only 60 were found. So tonight, as your eyes grow heavy and your breathing slows, imagine yourself floating slowly past the edge of Earth's atmosphere. The air grows thin, the blue fades to black, and there, a vast canvas of history and starlight stretches out before you. Every shimmering star is a chapter. Every faint glow is a story. If you gently press the notification bell, you will always know when the next journey begins. But for now, you do not need to do anything but listen, breathe, and drift. Let us travel together into the greatest silence humanity has ever discovered, into the place where nothingness speaks louder than stars. Welcome to the quiet side of the cosmos. There are moments in the history of science when the universe reveals something so unexpected, so impossible by all reasonable standards, that it forces us to question everything we thought we knew. The discovery of the Bootes void in 1981 was one of those moments. Imagine you are an astronomer in the early 80s, working with new technology that allows you to map not just where galaxies appear in the sky, but how far away they are. You are charting the three-dimensional structure of the universe for the first time, expecting to find galaxies sprinkled somewhat evenly across space, perhaps clumping here and there into clusters and filaments. You have theories, predictions, models that tell you roughly what you should see, and then you find nothing. Not a small gap, not a modest clearing between clusters, but a hole so vast that it seems to violate the very principles of how the universe should be structured. A spherical region of space 330 million light-years across, where your calculations tell you there should be at least 10,000 galaxies, perhaps even more. Instead, you find only 60 galaxies scattered like lost travelers in a desert larger than comprehension. At first, you think it must be a mistake. Perhaps the telescope missed something. Perhaps the data was corrupted. Perhaps you simply looked at the wrong patch of sky. You check the instruments. You recalculate. You observe again and again, and each time, the result is the same. The emptiness is real. This is not how the universe is supposed to work. Galaxies form from matter that clumps together under gravity. drawn by the invisible scaffolding of dark matter that threads through space. The cosmic web, as we call it, should be relatively uniform on the largest scales. Dense regions connected by filaments, with voids between them, yes, but voids of a manageable size. Nothing in the theories prepared anyone for this. The Butez void is not just empty, it is impossibly empty. If you were to take the volume of space it occupies and compare it to similar volumes elsewhere in the universe, you would expect to find thousands upon thousands of galaxies lighting up that darkness. Instead, there is silence. A silence so profound that it seems to echo. To understand just how shocking this discovery was, consider the scale. Our Milky Way galaxy is about 100,000 light-years across. The distance to our nearest large neighbour, Andromeda, is about 2.5 million light-years. The local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller companions, spans about 10 million light-years. The Butez void is 33 times larger than that entire neighbourhood. If our galaxy were placed in the centre of this void, the nearest other galaxies would be so far away that we would not have discovered them until the mid-20th century. For all of human history up until then, we would have looked out into the night sky and concluded that we were utterly alone in the universe. There would have been no debate about other galaxies because there would have been almost nothing to see. Think about what that means. Every telescope ever built, every observation ever made, every question ever asked about the cosmos would have been shaped by the overwhelming impression of solitude. The philosophical implications would have been staggering. Are we alone? The answer would seem to be yes. Not because life does not exist elsewhere, but because the structure of space itself had isolated us so completely that we could not even detect other galaxies. The discovery of the Butez void changed astronomy fundamentally. It forced scientists to confront the possibility that the universe is far stranger, far more extreme, far less predictable than the elegant models suggested. It opened questions that are still being answered today. What created such emptiness? How does something this large even form? What does it tell us about the distribution of dark matter, the influence of dark energy, the earliest moments after the Big Bang? But perhaps most unsettling was the realization that if a void this large can exist, what else might be out there? What other extremes, what other impossibilities might be hiding in the data we have not yet gathered? The Butez void is not unique. There are other voids scattered throughout the cosmos, but it remains one of the largest, one of the most studied, one of the most mysterious. It sits in the constellation Butez, the herdsman, a region of the northern sky visible from most of the northern hemisphere. On a clear night, if you know where to look, you can point your gaze toward that constellation and know that beyond the stars you see, beyond the limits of human vision, there stretches a desert of nothingness larger than anything we can truly comprehend. And yet, even in that nothingness, there is something. 60 galaxies, faint and scattered, drifting alone in the dark. They are survivors, relics, witnesses to whatever process carved out that immense hollow in the fabric of space. Each one is a story waiting to be understood. The Butez void does not just challenge our science, it challenges our imagination. It asks us to picture emptiness on a scale that defies mental imagery. It invites us to wonder what it would be like to live in one of those lonely galaxies, to look up at a night sky almost entirely devoid of other lights, to grow up believing that your island in the cosmos was all there was. This is the impossible beginning. A hole in the universe where none should exist. A silence in a symphony that should be unbroken. A mystery written in the language of absence. And as we step into this story, we step into one of the strangest chapters in the history of astronomy. a chapter that began with disbelief and continues today with wonder. The Bootes void is waiting, not with answers, but with questions, not with light, but with shadow, not with presence, but with absence. And in that absence, we will find something remarkable. To understand how the Bootes void was discovered, we need to travel back to a particular moment in the history of astronomy, a time when technology and ambition were finally catching up with the human desire to map the universe. It was the late 1970s and early 1980s, and a quiet revolution was taking place in observatories around the world. For centuries, astronomers had been limited to two-dimensional maps of the sky. They could see where galaxies appeared, scattered across the celestial sphere like stars on a dome. But they had no reliable way to measure depth, no way to know which galaxies were close and which were far. Distance is everything in astronomy. Without it, you cannot build a three-dimensional picture of the cosmos. You cannot understand structure. You cannot trace how galaxies cluster. You cannot see the architecture that underlies everything. You are like a map maker drawing coastlines without knowing which lands are islands and which are continents. But by the late 70s, astronomers had developed techniques to measure something called redshift, the stretching of light as it travels through an expanding universe. When a galaxy is moving away from us, its light shifts toward the red end of the spectrum. The more distant the galaxy, the greater the redshift. By measuring this shift carefully, astronomers could estimate how far away each galaxy was. For the first time in human history, it became possible to map the universe in 3 dimensions. This was the setting into which Robert Kirshner stepped. He was an astronomer at the University of Michigan, working alongside colleagues Augustus Oemler, Paul Schechter, and Stephen Schechtman. Together, they formed a team driven by a simple but profound goal. They wanted to chart the distribution of galaxies in space, to see how matter was arranged on the largest scales, to understand whether the universe was uniform or structured. Their tools were modest by today's standards. Telescopes equipped with spectrographs, instruments that could split light into its component wavelengths and measure the telltale redshift. Nights spent at observatories, gathering data one galaxy at a time, recording each redshift measurement by hand. The work was painstaking, slow, methodical. Each observation took time. Each galaxy was a data point, a single coordinate in the vast map they were building. They chose a region of the sky in the constellation Bootes to survey. It was not a particularly special region, no famous clusters, no bright landmarks. It was simply a patch of sky like any other, waiting to be explored. They pointed their telescopes and began measuring redshifts, expecting to find what everyone expected: galaxies scattered in the usual patterns, perhaps a cluster here, a filament there, the ordinary texture of the cosmic web. But as the data accumulated, something strange began to emerge. Imagine working on a jigsaw puzzle, placing piece after piece into position, watching the image slowly come together. You expect to see a landscape, a forest perhaps, with trees and hills filling the frame. But as you add more pieces, you realize that a large section of the puzzle is just blank. You check the box, you search the table, but the pieces are all there. The blank space is part of the picture. That is what Kirshner and his team were experiencing. As they plotted each galaxy's position in 3-dimensional space, the map showed clusters and filaments, just as expected. But in one region, the galaxies simply stopped. There was a vast spherical volume where almost nothing existed. The emptiness was not subtle. It was glaring. At first, they were skeptical. Science trains you to doubt your own results, to assume error before accepting revelation. Perhaps their survey had missed galaxies in that region. Perhaps the instruments had malfunctioned. Perhaps dust or some other obstruction had blocked their view. They checked and rechecked. They extended their observations, gathering more data, looking deeper. The void remained. By 1981, they could no longer deny what the data was telling them. There was an enormous hole in the universe, a region spanning hundreds of millions of light years where galaxies were shockingly scarce. They published their findings, and the astronomy community took notice. The paper itself was careful and measured, as scientific papers must be. It presented the data, described the methods, and noted the unexpected absence of galaxies in this region. But beneath the careful language, there was astonishment. This was not supposed to happen. The universe was not supposed to have gaps this large. The announcement landed in the midst of a broader conversation about cosmic structure. Other teams around the world were also mapping galaxies, building up a picture of how matter was distributed. Some were finding filaments, long chains of galaxies stretching across space. Others were finding walls, vast sheets of galaxies arranged in two-dimensional structures. The cosmic web was beginning to reveal itself. But the Bootes void was different. It was not a structure. It was an anti-structure, a place defined by what was missing rather than what was present. If filaments and walls were the continents of the universe, then the Bootes void was an ocean, but an ocean far larger than anyone had predicted. The setting of this discovery matters because it shaped how the void was understood. This was an era when computers were just beginning to be powerful enough to run simulations of cosmic structure. Scientists could model how matter clumped together under gravity, starting from the nearly uniform conditions of the early universe and evolving forward through billions of years. These simulations predicted voids, yes, but small ones. Nothing like Bootes. It was also an era of debate about dark matter. Astronomers had known for decades that galaxies contained more mass than could be accounted for by visible stars and gas. Something invisible was holding them together. The term dark matter had been coined, and theories were being developed about what it might be and how it shaped the universe. The discovery of the Bootes void added fuel to that debate. If dark matter shaped the cosmic web, then what did such an enormous void say about how dark matter was? Distributed? Was there simply less of it in that region? Or was something else at play? The setting was also one of technological limitation. Today, astronomers can map millions of galaxies in automated surveys, building detailed three-dimensional maps with relative ease. But in the early 80s, every galaxy was a hard-won data point. The fact that Kirshner and his team were able to identify the void at all was a testament to their persistence. They spent countless nights in the cold domes of observatories, guiding telescopes by hand, recording spectra on photographic plates. It was labor-intensive, exhausting work, and yet they persisted. They persisted because they were explorers. The universe was still largely unmapped, and every new redshift measurement was a step into the unknown. They did not know they would find a void. They were simply charting the territory, letting the data reveal what was there. And what the data revealed was one of the strangest discoveries in history of astronomy. The setting also matters, because it reminds us that discovery is rarely dramatic in the moment. There was no sudden revelation, no eureka moment. The void emerged gradually, as data accumulated, as patterns became clear. It was only in retrospect, after all the observations had been gathered and analysed, that the team could step back and say, "We have found something extraordinary." This is how science works. Not in flashes of insight, but in patient accumulation of evidence. Not in grand pronouncements, but in careful papers published in journals. The Bootes void did not announce itself with fanfare. It whispered into existence through data points on a graph. through galaxies that were not there. This was before the internet, before social media, before science news spread instantly around the world. The discovery of the void was reported in scientific journals and mentioned in a few newspaper articles, but it did not capture the public imagination immediately. It was only later, as more surveys confirmed the void and as its implications became clearer, that people began to appreciate just how strange it was. The void itself is a feature of patience. It does not dazzle with light. It does not announce itself with explosions or fireworks. It is defined by absence, by silence, by the slow realization that something is missing. The setting of the discovery shaped the story in another way. It made the void a collaborative achievement. Kirshner and his colleagues were part of a broader community of astronomers, all working toward the same goal: mapping the universe. Their discovery built on decades of prior work, on the development of redshift measurement techniques, on improvements in telescopes and instruments, on theoretical predictions about cosmic structure. No one person discovered the Bouteille's void. It emerged from the collective effort of a generation of astronomers who had the ambition to map the cosmos and the patience to do the work. And so, the setting was this: the early 1980s, a time of technological transition, a moment when the universe was just beginning to reveal its three-dimensional structure. A team of dedicated astronomers in Michigan, working with modest tools and enormous ambition. And a discovery that would challenge everything we thought we knew about how the universe was put together. The stage was set. The tools were ready. The observations were made. And what emerged from that patient, methodical work was a hole in the universe, waiting to be understood. There is a particular kind of silence that falls over a room when scientists realize they have found something they cannot immediately explain. It is not the silence of confusion, nor the silence of disappointment. It is the silence of dawning wonder, the moment when the universe has shown you something new, and you are trying to absorb what it means. That silence fell over Robert Kirshner and his team as they looked at their data. They had been measuring redshifts for months, building up a catalogue of galaxies in the Bouteille region. Each night, at the telescope, added more points to their three-dimensional map, and slowly, steadily, a pattern was emerging. Clusters appeared where galaxies huddled together. Filaments stretched between them, thin chains of light connecting dense nodes. This was expected. This was what the models predicted. But there was also something else. A gap, a hollow, a region where the galaxies simply stopped. At first, it was easy to dismiss. Perhaps they had not looked deeply enough in that direction. Perhaps fainter galaxies were hiding there, just below the detection threshold. Perhaps it was an artifact of their survey strategy, a consequence of which parts of the sky they had chosen to observe. But, as more data came in, the gap grew larger. It was not a trick of observation. It was real. The moment of discovery was not dramatic. There was no sudden flash of insight, no single observation that revealed everything. Instead, it was a gradual accumulation of evidence, a slow realization that something extraordinary was hiding in plain sight. One of the team members, looking at the plotted data, must have been the first to say it aloud. There is almost nothing here, and the others would have gathered around, studying the plot, checking the numbers, confirming what their eyes were telling them. A spherical volume of space, enormous in extent, almost devoid of galaxies. They ran the numbers. Based on the density of galaxies in surrounding regions, they calculated how many should exist in this volume. The answer was thousands, perhaps 10,000 or more. They counted how many they had actually found. 60, maybe a few dozen more if they stretched the definition of where the void began and ended. But no matter how they counted, The discrepancy was staggering. 60 galaxies where 10,000 should be. This was not a small anomaly. This was not a statistical fluctuation. This was a hole in the universe. The discovery sparked questions immediately. The team knew they had found something important, but they did not yet know what it meant. Was this a unique feature, a one-of-a-kind oddity? Or were there other voids like this scattered throughout the cosmos, waiting to be discovered? If voids this large could exist, what did that say about the processes that shaped the universe? They also faced a more immediate challenge, convincing others that the void was real. In science, extraordinary claims require extraordinary evidence. And claiming that there was a hole in the universe 330 million light-years across was certainly extraordinary. They needed to be sure of their data before going public. So they checked everything. They re-examined their observations, making sure that no instrumental errors had crept in. They compared their results with other surveys, looking for confirmation or contradiction. They ran statistical tests, calculating the probability that such a void could arise by chance. Every test pointed to the same conclusion. The void was real. The spark of mystery came not just from the existence of the void, but from its implications. If galaxies form from the gravitational collapse of matter, guided by the invisible scaffolding of dark matter, then a void this large implied something profound about the initial conditions of the universe. It suggested that, in the earliest moments after the Big Bang, there must have been a region where matter was significantly underdense, a seed of emptiness that grew over billions of years. Why would such a large, underdense region exist? The cosmic microwave background, the afterglow of the Big Bang, showed that matter was distributed almost uniformly in the early universe. Tiny fluctuations, yes, but nothing that seemed capable of producing a void this vast. The void was pushing the boundaries of what the models allowed. The discovery also sparked excitement among the team. This was what they had been searching for. Not specifically a void, but something new. Some feature of the universe that had never been seen before. Astronomy is filled with routine observations, measuring this star, cataloguing that galaxy. But every so often, the data reveals something unexpected. And those moments are what keep astronomers going through the long nights and painstaking work. The Bootes void was one of those moments. As word of the discovery began to spread through the astronomy community, reactions were mixed. Some were skeptical, suggesting that the void might be an artifact of incomplete data. Others were intrigued, recognizing that if the void was real, it represented a major challenge to existing theories. Still, others were simply curious, wondering what might be hiding inside that vast emptiness. The team prepared their paper carefully. In science, the way you present a discovery matters almost as much as the discovery itself. They needed to lay out the data clearly, explain their methods thoroughly, and address potential objections before they were raised. The paper was titled simply, describing the survey and noting the presence of a large void in the Bootes region. It was published in 1981, and it marked the moment when the void officially entered the scientific record. But the discovery was only the beginning. The real work would come in the years that followed, as astronomers tried to understand what the void meant. In the immediate aftermath, other teams began to look for similar features in their own data. If one void this large could exist, surely there must be others. And indeed, as more surveys were conducted, more voids were found. The Bootes void was not unique, but it remained one of the largest and most striking examples. The spark of mystery also ignited imaginations beyond the scientific community. When news of the void reached the public, it captured attention in a way that few astronomical discoveries do. A hole in the universe, The phrase itself was evocative, suggesting something almost supernatural, as if reality itself had been torn. Science fiction writers seized on the concept, philosophers pondered its implications, and ordinary people found themselves wondering what it would be like to live in such emptiness. The discovery also highlighted a fundamental truth about science. We do not fully understand the universe. Despite decades of observations, despite powerful theories and sophisticated models, nature can still surprise us. The Booty's Void was a reminder that the cosmos is stranger and more varied than we often assume. For Kirshner and his team, the discovery was both a triumph and a beginning. They had mapped a region of the universe no one had mapped before, and they had found something extraordinary. But now came the harder part, figuring out what it meant. The spark of mystery was lit. The void had been discovered, and the questions it raised would occupy astronomers for decades to come. What created such a massive emptiness? How did it fit into the larger story of cosmic structure? Were there clues hidden inside, waiting to be uncovered? These questions could not be answered immediately. They required more data, deeper observations, better simulations. They required patience and persistence, the same qualities that had led to the discovery in the first place. But the spark was there. The mystery was real, and the journey to understand it had only just begun. In years to come, the Booty's Void would be studied from every angle. Telescopes would peer deeper into its interior, searching for faint galaxies. Simulations would attempt to recreate its formation. Theories would be proposed and tested, and gradually, piece by piece, the picture would become clearer. But in that moment of discovery, in the silence that fell over the team as they realized what they had found, there was only wonder. They had charted a map of the universe and found a hole where none should be. They had touched something profound, something that spoke to the deepest questions about existence and structure and the nature of reality itself. The spark of mystery had ignited, and it burned still. When the paper announcing the Booty's Void was published, the response from the scientific community was immediate and varied. Some astronomers were fascinated, recognizing that this discovery opened new questions about cosmic structure. Others were skeptical, suspecting that the void might be an artifact of how the survey was conducted, and still others were simply stunned, unable to reconcile the existence of such a massive empty region with their understanding of how the universe should be organized. This mixture of awe and disbelief is common in science when something truly unexpected is discovered. It reflects the tension between openness to new ideas and the need for rigorous skepticism. Extraordinary claims, as Carl Sagan famously said, require extraordinary evidence, and the claim that there was a hole in the universe 330 million light-years across was certainly extraordinary. The first response from many astronomers was to question the data itself. Could there be an error in the redshift measurements? Redshifts are calculated by identifying specific spectral lines in a galaxy's light and measuring how much they have shifted toward the red end of the spectrum. It is a well-established technique, but it requires careful calibration. If the measurements were off, even slightly, the apparent distances to galaxies could be wrong, and the void might disappear. Kirshner and his team had anticipated this objection. They had double-checked their measurements, comparing their results with other surveys and looking for systematic errors. The redshifts were solid. The void was real. Another objection came from those who wondered whether the survey had simply missed galaxies in that region. Perhaps the void was not actually empty, but merely appeared that way because fainter galaxies had gone undetected. This was a reasonable concern. After all, telescopes have limits. They can only see objects above a certain brightness threshold. If the void contained many faint dwarf galaxies, too dim to detect with the instruments of the time, then it might not be as empty as it appeared. This objection was harder to dismiss outright. It was true that the survey could only detect galaxies above a certain brightness, but the team had estimated how many faint galaxies they might be missing, and even accounting for that, the void remained strikingly underpopulated. There should still be thousands of galaxies visible, not just 60. The emptiness was real, even if a few faint galaxies lurked below the detection limit. A third objection was more subtle. Some suggested that the void might be a statistical fluke, an unlucky roll of the cosmic dice. After all, if you survey enough regions of space, you might eventually find one where galaxies happen to be scarce, just by chance. This argument had some merit, but it ran into a problem. The void was too large to be easily dismissed as random chance. Statistical models showed that a void this size should be extremely rare if the universe were truly uniform on large scales. Its existence suggested that the universe was not uniform, that there were real structures and anti-structures shaping the distribution of matter. Despite these objections, the tide of opinion gradually shifted toward acceptance. As other teams conducted their own surveys and found similar voids elsewhere in the universe, it became clear that the Bootes void was not an isolated anomaly. Voids were a real and common feature of cosmic structure. They were part of the pattern, not a mistake in the data. But acceptance did not mean understanding. Even as astronomers agreed that the void was real, they struggled to explain it. How could such an enormous region be so underdense? What process could carve out such a massive hollow in the fabric of space? The awe came from the scale. 330 million light-years. To put that in perspective, the entire observable universe is about 93 billion light-years across. The Bootes void, while only a fraction of that, is still incomprehensibly large. If you could travel at the speed of light, it would take you 330 million years to cross from one side to the other. That is longer than the age of the dinosaurs, longer than most species on Earth have existed. To imagine such a span of emptiness, almost devoid of galaxies, was to confront the sheer strangeness of the universe. We are used to thinking of space as filled with stars and galaxies, as teeming with light. The void challenged that, to assumption. It showed that the universe also contains vast deserts, regions where light is scarce and silence reigns. The disbelief, meanwhile, came from the challenge the void posed to existing theories. By the early 80s, cosmologists had developed a fairly detailed picture of how cosmic structure formed. After the Big Bang, matter was distributed almost uniformly, with tiny fluctuations imprinted by quantum processes in the earliest moments. Over billions of years, gravity amplified these fluctuations. Denser regions pulled in more matter, forming galaxies and clusters. Less dense regions lost matter to their neighbours, forming voids. This picture predicted voids, but not ones this large. Most simulations produced voids measuring tens of millions of light-years across, perhaps 100 million at most. The Bootes void, at over 300 million, was an outlier. It stretched the models to their limits. Some scientists wondered whether the void might be evidence of new physics. Perhaps dark matter behaved differently than expected, or perhaps there were processes in the early universe that had not been accounted for. The void became a test case, a benchmark that any complete theory of cosmic structure would have to explain. The emotional response was also significant. For many astronomers, the discovery of the void was humbling. It reminded them that despite decades of progress, despite powerful telescopes and sophisticated theories, the universe could still surprise them. It was a lesson in intellectual humility. a reminder that our understanding is always provisional, always subject to revision in light of new evidence. For others, the void was inspiring. It represented the frontier of knowledge, the edge of what was known. It was a mystery waiting to be solved, and mysteries are what drive science forward. The void was not just a problem, it was an opportunity, a chance to learn something fundamentally new about how the cosmos works. The public response, when news of the void reached beyond the scientific community, was equally mixed. Some found the idea unsettling. A hole in the universe sounded ominous, almost threatening. It evoked images of emptiness and isolation, of vast deserts where nothing lived. Others found it fascinating, a cosmic curiosity that spoke to the diversity of the universe. Science fiction writers, in particular, latched onto the void. Stories were written about explorers venturing into its depths, about civilizations living in the lonely galaxies scattered within, about secrets hidden in the emptiness. The void became a canvas for speculation, a blank space where imagination could run wild. But for the astronomers who discovered it, the first response was simpler. It was the response of explorers who had ventured into uncharted territory and found something unexpected. There was pride in the discovery, satisfaction in having done the work carefully and thoroughly. But there was also wonder, the kind that comes from realizing that the universe is larger and stranger than you imagined. The awe and disbelief would fade over time as the void became a familiar feature of the cosmic landscape. But in those first years after the discovery, it remained deeply surprising. A reminder that nature does not always conform to our expectations. The universe is under no obligation to make sense to us. It simply is. And sometimes what it is includes massive voids where galaxies should be but are not. The first response, then, was not a single thing but a spectrum of reactions, from skepticism to wonder, from technical objections to philosophical musings. It reflected the fact that the void was not just a scientific discovery but a cultural moment, a point where our understanding of the cosmos shifted slightly, making room for something new and strange. And as the initial shock wore off, the real work began. Astronomers would spend decades trying to understand the void, to fit it into the larger story of cosmic evolution. But the first response, that mixture of awe and disbelief, set the tone. It established that the void was not just another data point, but something special, something that deserved careful attention and deep thought. The universe had spoken, and we were still learning to listen. The Bootes void presented science with a paradox. On one hand, it was entirely consistent with the known laws of physics. Gravity, dark matter, the expansion of the universe, all of these forces could, in theory, produce voids. On the other hand, the sheer scale of the Bootes void strained the predictions of those same laws. It was both explainable and inexplicable, both natural and impossible. This contradiction lies at the heart of what makes the void so fascinating. It is not that the void breaks the rules, it is that it pushes them to their absolute limits, occupying a space where the rules barely hold, where the universe reveals just how extreme it can be while still obeying its own internal logic. Let us start with what science says should happen. In the early universe, moments after the Big Bang, matter was distributed almost uniformly across space. Almost, but not quite. Tiny fluctuations existed, regions where density was slightly higher or slightly lower than average. These fluctuations were imprinted by quantum processes during the era of cosmic inflation, when the universe expanded faster than the speed of light for a brief instant. Over billions of years, gravity went to work on those fluctuations. Denser regions pulled in more matter, growing denser still. Less dense regions lost matter to their neighbors, growing emptier. This process, amplified by the invisible presence of dark matter, created the cosmic web we see today. Filaments and clusters of galaxies threading through enormous voids. Voids, then, are a natural consequence of structure formation. They are the regions that got left behind, the places where the initial underdensity was just enough that matter flowed outward rather than inward. According to this picture, voids should exist. They are part of the pattern. But here is the problem. The models that predict voids also predict their typical size. Most voids should be modest, measuring tens of millions of light years across. Some might reach 100 million, but 330 million? That is an outlier, a statistical extreme that the models do not produce easily. To understand why, think about probability. If you flip a coin 10 times, you expect roughly 5 heads and 5 tails. Sometimes you might get 6 heads, or 7. Rarely, you might get 8 or 9. But getting 10 heads in a row is extremely unlikely. It is not impossible, but it happens so rarely that if you see it, you start to wonder whether the coin is fair. The Bootes void is like flipping 10 heads in a row. It is not impossible within the framework of known physics, but it is so rare that it forces scientists to ask uncomfortable questions. Is the model missing something? Are the initial conditions different than assumed? Or are we simply witnessing an extreme statistical fluctuation, a cosmic roll of the dice that happened to come up in an unusual way? This is the contradiction. Science can explain the void in principle, but struggles to explain it in practice. The void fits within the framework, but just barely. It occupies the edge of what the models allow, the boundary between the expected and the extraordinary. The mystery deepens when you consider dark matter. Dark matter is the invisible scaffolding that holds the universe together, the mass that governs how galaxies cluster and how voids expand. If the Bootes void is so large, it implies that the dark matter in that region was significantly underdense from the very beginning. But why would such a large patch of space have so little dark matter? One possibility is that the fluctuations imprinted during cosmic inflation were not as uniform as we think. Perhaps inflation itself had variations, regions where it lasted slightly longer or shorter, leading to larger or smaller fluctuations in matter density. If the Bootes region experienced an unusually large underdensity during inflation, that could explain the void. But this is speculative. We have no direct evidence that inflation worked this way. Another possibility is that multiple smaller voids merged over time, creating one giant void. This is more plausible. Computer simulations show that voids can grow and combine, much like soap bubbles joining together. If several moderate voids happened to be near each other in the early universe, they might have merged into the Bootes void we see today. But even this explanation requires a certain amount of luck, a particular arrangement of initial conditions that is rare but not impossible. The contradiction also extends to philosophy. Science seeks to explain the universe in terms of laws and patterns to reduce complexity to underlying principles. But the Bootes void resists easy explanation. It is a reminder that even within a lawful universe, extreme outcomes can occur. It challenges the idea that everything can be predicted, that given enough information about initial conditions, we could calculate exactly how the universe would turn out. In practice, the universe contains too much complexity, too much randomness for such perfect prediction. The Bootes void may be an example of this irreducible complexity, a feature that could only be predicted in the broadest statistical sense, not in its specific details. There is also a deeper mystery lurking beneath the surface. If the void is real, If it truly is as empty as it appears, then what does that emptiness contain? We know that space is never truly empty. Even in the vacuum of intergalactic space, there are particles popping in and out of existence. Photons travelling from distant sources, neutrinos streaming through at nearly the speed of light. And of course, there is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy is thought to be uniform, permeating all of space equally. But what if it is not? What if dark energy varies from place to place, and the Bootes void is a region where it is slightly stronger or weaker than average? This could affect how the void expands, how matter flows out of it, even how time itself passes within it. Such variations are highly speculative, but the void forces us to consider possibilities that would otherwise seem far-fetched. The contradiction between science and mystery is not a failure of science. It is a feature of how science works. Science is not about having all the answers. It is about asking the right questions, gathering evidence, and refining our understanding over time. The Bootes void is a question written in the structure of the universe, a puzzle that invites us to think more deeply about cosmic evolution. In some ways, the void is a gift to cosmology. It provides a test case, a benchmark against which theories can be measured. Any model of structure formation that cannot produce a void like Bootes is incomplete. The void does not break the rules, but it shows us where the rules are stretched thin, where our understanding is least certain. The mystery also has emotional weight. There is something unsettling about a region of space so empty, so barren of the light and life we associate with galaxies. It feels wrong, as if the universe made a mistake, left a blank spot on the canvas. But the universe does not make mistakes. It simply is. And what it is includes both abundance and absence, both presence and void. This contradiction between what should be and what is, between prediction and observation, between understanding and mystery, is what keeps the Bootes void alive in the scientific imagination. It is not a problem to be solved once and forgotten. It is an ongoing conversation, a dialogue between theory and reality. And perhaps that is the deepest truth the void reveals. Science and mystery are not opposites. They are partners. Science thrives on mystery, on the unknown, on the places where our understanding breaks down and we are forced to think anew. The Bootes void is one of those places. It challenges us, provokes us, reminds us that the universe is always more than we think it is. The contradiction will not be resolved easily. It will take more observations, deeper simulations, better theories, but in the meantime, the void sits there in the constellation Bootes, a silent testament to the strangeness of existence, a hole in the universe that is both explained and inexplicable, both natural and impossible. And in that contradiction, we find not frustration, but wonder. When faced with something as strange as the Bootes void, scientists do what they always do. They begin building theories, constructing explanations that might account for what has been observed. But because the void is so extreme, so close to the edge of what the models predict, the theories that emerged were diverse, sometimes contradictory, and always speculative. This is where minds divide. Different researchers, approaching the problem from different angles, proposed different solutions. Some theories were conservative, suggesting that the void was simply an extreme but natural outcome of ordinary processes. Others were more radical, invoking new physics or unusual conditions in the early universe. And still others occupied a middle ground, proposing mechanisms that were plausible but not yet proven. Let us explore these theories, not as definitive answers, but as the landscape of ideas that the void has inspired. The first and most straightforward theory is that the Bootes void is simply a statistical outlier. In any large enough system, extreme events will occasionally occur. Flip a coin enough times, and you will eventually get a long string of heads. Survey enough volumes of space, and you will eventually find one where galaxies are unusually scarce. According to this view, there is nothing fundamentally mysterious about the void. It is rare, yes, but not impossible. It is what happens when random fluctuations in the early universe happen to produce an especially large underdense region. This theory has the advantage of simplicity. It does not require new physics or special conditions. It simply says that the void is an expected, if uncommon, outcome of the processes we already understand. The downside is that it feels somewhat unsatisfying. It explains the void by appealing to luck, to randomness. And while randomness is a legitimate explanation, it leaves us wondering whether there might be more to the story. A second theory focuses on dark matter. Dark matter makes up about 85% of the matter in the universe, and its gravitational pull is what shapes the cosmic web. If the distribution of dark matter in the early universe was unusually uneven in the Bootes region, that could explain the void. Perhaps there was a large patch of space where dark matter was significantly underdense, and as a result, ordinary matter had nothing to clump around. Over billions of years, this underdensity would grow as matter flowed out toward denser regions, leaving behind the vast emptiness we see today. This theory is appealing because it ties the void directly to dark matter, the invisible scaffolding of the universe. It suggests that by studying the void, we can learn something about how dark matter is distributed on the largest scales. The challenge is that we have no direct observations of dark matter. We can only infer its presence through its gravitational effects. So, while this theory is plausible, it is difficult to test directly. A third theory invokes cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang. During inflation, quantum fluctuations were stretched to cosmic scales, creating the seeds of structure that would later grow into galaxies and voids. Most models of inflation predict fluctuations of a certain size and amplitude. But what if inflation was not perfectly uniform? What if it had variations, regions where the fluctuations were larger or smaller than average? If the Bootes region experienced an unusually large underdensity during inflation, that could explain the void. This theory pushes inflation to its limits, suggesting that the process was more complex than the simplest models allow. It is an attractive idea because it ties the void to the very earliest moments of the universe, making it a fossil of creation itself. But it is also speculative, requiring variations in inflation that we have not yet detected. A fourth theory suggests that multiple smaller voids merged over time to create the Bootes void. In simulations of structure formation, voids can grow and combine, much like bubbles in foam. If several moderate-sized voids happen to be near each other, in the early universe, they might have gradually merged, creating one enormous void. This theory has the advantage of being testable. By studying the distribution of galaxies around the void and the properties of the few galaxies inside it, astronomers can look for evidence of multiple merged voids. This is one of the more plausible explanations, and it aligns well with observations. The Bootes void may not be a single giant bubble, but rather several overlapping cavities that together create the appearance of one massive void. If true, it would mean the void is less of an outlier than it seems, simply an extreme example of a common process. A fifth, more speculative theory involves dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy is thought to be uniform, filling all of space equally. But what if it is not? What if there are regions where dark energy is slightly stronger or weaker, and those variations affect how voids grow? In regions with stronger dark energy, voids might expand faster, growing larger than they would otherwise. The Butes void could be one such region. This theory is highly speculative. We have no direct evidence that dark energy varies from place to place. But if it does, voids like Butes would be the best places to detect those variations. By measuring how the void expands over time and comparing it to predictions, astronomers could potentially test whether dark energy is truly uniform or not. A sixth theory, more exotic still, suggests that the void might be evidence of new physics beyond the standard model. Perhaps there are particles or forces we have not yet discovered, and they played a role in creating the void. Perhaps gravity behaves differently on cosmic scales than we think. These ideas are on the fringe of mainstream science, but they cannot be dismissed entirely. The void is extreme enough that it might be revealing something fundamental about the universe that we have missed. Division of minds is not just about which theory is correct. It is also about how scientists approach the unknown. Some prefer conservative explanations, sticking to known physics and invoking randomness when necessary. Others are more willing to consider radical ideas, to entertain the possibility that the void is telling us something genuinely new. Both approaches are valuable. Science needs both caution and boldness, both skepticism and imagination. What unites these theories is that they all take the void seriously. They recognize that it is not just an oddity to be dismissed, but a feature of the universe that demands explanation. And in trying to explain it, scientists are forced to confront the limits of their understanding, to push their models to the breaking point and see what emerges. The theories also reflect the fact that the void is not an isolated phenomenon. It sits within a larger context, the cosmic web, the history of the universe, the interplay of dark matter and dark energy. Understanding the void means understanding how all these pieces fit together, how the universe evolved from a nearly uniform state to the complex, textured landscape we see today. As more data has been gathered, some theories have gained support while others have faded. The idea that the void is a merged structure of smaller voids has become increasingly plausible. The statistical outlier explanation remains a fallback, a reminder that not everything has a deep cause, and the more exotic theories remain on the table, waiting for evidence that might support or refute them. But even now, decades after the discovery, no single theory has definitively explained the Butes void. It remains an open question, a puzzle that continues to challenge and inspire. And perhaps that is appropriate. The universe is not obligated to provide us with easy answers. Some mysteries take time to unravel, and the void may be one of them. The division of minds, then, is not a weakness, but a strength. It shows that science is alive, that ideas are being tested and refined, that the conversation continues. The void has sparked a dialogue that spans decades and involves hundreds of researchers, each contributing a piece to the larger puzzle. And as that dialogue continues, we inch closer to understanding not just the void itself, but the deeper principles that govern the cosmos. The theories may divide us in the short term, but in the long term, they unite us in a common quest, a shared curiosity about the nature of existence. The Butes void is not just a hole in space, it is a hole in our knowledge, a gap that invites us to think more deeply, to question more carefully, to imagine more boldly. And in that gap, minds divide, theories flourish, and science moves forward. Discovery is only the beginning. Once something extraordinary has been found, the real work begins. The Butes void, having been announced to the scientific world in 1981, became the focus of decades of investigation. Astronomers wanted to know everything about it. How large was it really? What galaxies existed inside? How did it compare to other voids? And most importantly, what could it teach us about the universe? The pursuit of these answers required patience, technology, and dedication. It meant returning to the void again and again, with better instruments each time, gathering more data, refining measurements, slowly building up a complete picture of this strange cosmic desert. The first priority was to map the void more precisely. The initial discovery had identified its existence and estimated its size, but the boundaries were not yet clear. Where exactly did the void begin and end? Was it a perfect sphere, or did it have an irregular shape? To answer these questions, astronomers needed to measure redshifts for thousands of galaxies surrounding the void, creating a three-dimensional map that would reveal its true extent. This work was painstaking. Each galaxy required its own spectrum, its own redshift measurement. In the early days, this meant long nights at telescopes, guiding instruments by hand, recording data on photographic plates. As technology improved, the process became faster and more automated, but it still required enormous effort. Galaxy surveys grew larger and more comprehensive, and with each new survey, the picture of the void became sharper. By the late 1980s and into the 1990s, surveys like the CFA Redshift Survey and the Las Campanas Redshift Survey were mapping huge swaths of the sky, measuring redshifts for tens of thousands of galaxies. These surveys confirmed that the Bootes void was real and helped define its boundaries more precisely. They also revealed something else. The void was not alone. Other large voids existed throughout the universe, and together they formed part of the cosmic web, the foam-like structure that defines how matter is distributed on the largest scales. The next phase of investigation focused on what was inside the void. The initial discovery had found only a few dozen galaxies, but were there more? Could deeper observations reveal fainter galaxies that had been missed? This question was important because it would determine just how empty the void really was. Astronomers pointed powerful telescopes into the heart of the void, searching for anything that might be lurking there. They found a few additional galaxies, faint dwarf systems that had been too dim to detect in earlier surveys. But even with these additions, the void remained strikingly underpopulated. Where thousands of galaxies should exist, only around 60 were found. The emptiness was real. The galaxies that were found became objects of intense study. What were they like? How did they compare to galaxies in denser regions? Researchers discovered that void galaxies tended to be smaller, bluer, and more gas-rich than their counterparts in clusters. They were still forming stars, but at a slower, steadier pace. They had not undergone the violent collisions and mergers that shape galaxies in crowded environments. In a sense, they were pristine, preserved examples of what galaxies look like when left largely undisturbed. This finding was significant. It suggested that environment plays a crucial role in galactic evolution. Galaxies in clusters are constantly buffeted by their neighbours, stripped of gas, merged and transformed. Void galaxies, by contrast, evolve in isolation, their development driven by internal processes rather than external forces. By studying them, astronomers could learn what galaxies do when left alone. The investigation also turned to dark matter. If the void was so underdense, what did that say about the distribution of dark matter? Researchers used gravitational lensing, a technique where the bending of light by mass reveals the presence of invisible matter, to probe the void. They found that dark matter was indeed less concentrated in the void than in surrounding regions. confirming that the emptiness extended beyond just visible galaxies. The invisible scaffolding of the universe was sparse there as well. Computer simulations became another crucial tool in the investigation. By running models of cosmic structure formation, researchers could simulate how voids form and evolve over billions of years. They could test different initial conditions, different amounts of dark matter, different values for dark energy, and see which scenarios produced voids like Bootes. These simulations revealed that voids are dynamic structures. They grow over time as matter flows out of them toward denser regions. Galaxies on the edges of voids are pushed outward, while the interior becomes increasingly empty. The simulations also showed that large voids like Bootes can form through the merger of smaller voids, much like bubbles combining in foam. This supported the idea that the void was not a single, unique structure, but an extreme example of a common process. One of the most intriguing aspects of the investigation was the search for effects the void might have on light passing through it. According to general relativity, light is affected by the gravitational fields it passes through. In dense regions, light loses energy, climbing out of gravitational wells. In underdense regions like voids, light gains energy falling into the shallower wells and then loses less climbing out. This effect, called the integrated Sachs-Wolf effect, can be measured by comparing the cosmic microwave background radiation to the distribution of matter. Astronomers looked for this signature in the Bootes void. They found subtle hints that the void was indeed leaving an imprint on the cosmic microwave background. A faint cold spot where photons had lost energy passing through the underdense region. This was not dramatic evidence, but it was consistent with the idea that the void was real and massive enough to affect light travelling through it. The pursuit also involved comparing the Bootes void to other voids. As more surveys mapped the universe, dozens of large voids were identified. Some were comparable in size to Bootes, others smaller. By studying the statistical properties of voids, their sizes, shapes, and distributions, astronomers could test theories of structure formation. If the models predicted too few large voids, or too many, that would indicate a problem with the underlying physics. The results were encouraging. The models, when properly tuned, could reproduce the observed distribution of voids reasonably well. The Bootes void was rare, but not inexplicable. It sat at the tail end of the distribution, an extreme example, but still within the range of what the models allowed. Another line of investigation focused on the expansion of the void. Voids do not just sit there, they grow as the universe expands and as matter continues to flow out of them. By measuring the velocities of galaxies around the void, astronomers could track how it was evolving. This information was valuable because it provided a way to test theories of dark energy. If dark energy drives the accelerated expansion of the universe, then voids should expand faster than the universe as a whole. Measuring this acceleration could help constrain the properties of dark energy. The pursuit of understanding the Bootes void has not been the work of a single team or a single decade. It has been a collective effort spanning generations of astronomers, each building on the work of those who came before. The initial discovery in 1981 opened the door. Subsequent surveys in the 90s and 2000s refined the picture. And modern telescopes and surveys, like the Sloan Digital Sky Survey and the upcoming Vera Rubin Observatory, continue to add new layers of detail. The investigation has also revealed something profound about science itself. Progress is not always linear. Sometimes you discover something and immediately understand it. Other times, understanding comes slowly, piece by piece, as new data and new ideas converge. The Bootes void has been the latter kind of discovery. Decades after it was first found, we are still learning from it. still refining our theories, still uncovering new details. The pursuit continues because the void has not yet revealed all its secrets. There are still questions unanswered. Are there faint structures inside the void that we have not yet detected? Are there subtle variations in dark energy that affect how it expands? What can the void tell us about the earliest moments of the universe, about the quantum fluctuations that seeded all structure? These questions drive the investigation forward. They ensure that the void remains not just a historical curiosity, but an active area of research. New instruments, new techniques, new ideas, all are brought to bear on this cosmic mystery. And in pursuing these answers, astronomers are doing more than just studying one particular void. They are learning how the universe works on the largest scales, how structure forms, how dark matter and dark energy shape the cosmos. The Bootes void is a laboratory, a natural experiment that the universe has provided, and by investigating it thoroughly, we gain insights that extend far beyond this one region of space. The pursuit is also deeply human. It reflects our desire to understand, our refusal to accept mystery as an endpoint, our insistence on asking questions even when the answers are difficult. The void does not explain itself. It simply exists, but we, curious beings that we are, cannot leave it at that. We must investigate, must probe, must seek to understand, and so the investigation continues. Telescopes point toward Bootes, data accumulates, papers are published, conferences are held, and slowly, steadily, the picture becomes clearer. The void is not giving up its secrets easily, but it is giving them up. And with each new piece of information, we come a little closer to understanding one of the strangest features of the universe. The pursuit is far from over. It may never truly be over. The universe is vast, and the questions it raises are endless. But that is the beauty of science. It is not about reaching a final answer. It is about the journey, the process of discovery, the slow accumulation of knowledge. And in that journey, the Bootes void stands as a milestone, a reminder that even the emptiest places in the universe have stories to tell, if only we have the patience and dedication to listen. In science, data is everything. Theories can be elegant, ideas can be compelling, but without data to support them, they remain speculation. The Bootes void has been studied through decades of observations, and the data that has accumulated tells a story written in redshifts and spectra, in galaxy counts and distributions, in the subtle patterns left by invisible forces. Let us examine the data, the clues, and fragments that have been gathered, and see what they reveal. The most fundamental piece of data is the size of the void. Early estimates placed it at around 300 million light-years across, making it one of the largest voids known. More recent measurements, using larger surveys and more precise techniques, have refined this estimate. The void is roughly spherical, though not perfectly so, with a diameter that varies depending on exactly where you draw the boundary. Some measurements suggest it could be as large as 330 million light-years across, while others give slightly smaller values. The exact size matters because it determines how unusual the void is. A 300 million light-year void is extremely rare but not impossible within the framework of known physics. A 400 million light-year void would be even rarer, pushing harder against the limits of what the models predict. The data suggests that the Bootes void sits right at the edge of what we expect, large enough to be surprising, but not so large as to be inexplicable. Another crucial piece of data is the galaxy count. How many galaxies exist inside the void? The initial discovery found around 60. Subsequent deeper surveys have added a few more, bringing the total to perhaps 70 or 80, depending on how you define the void's boundaries. This is still far fewer than expected. Based on the average density of galaxies in the universe, a volume this size should contain thousands, perhaps 10,000 or more. The discrepancy is stark. The void is underdense by a factor of 10 or more compared to the cosmic average. That is not just a little bit empty. That is profoundly empty. The galaxies that do exist inside the void have been studied in detail. Spectroscopy reveals their compositions, their star formation rates, their masses. The data shows that void galaxies tend to be smaller and less massive than galaxies in clusters. Many are dwarf galaxies, modest systems containing billions rather than hundreds of billions of stars. They are also bluer on average, indicating that they are still actively forming stars. In clusters, many galaxies have exhausted their gas supplies, turning red as their star formation ceases. Void galaxies, by contrast, have retained their gas, allowing them to continue forming stars at a steady pace. This difference is telling. It suggests that the environment in which a galaxy lives shapes its evolution. In dense regions, galaxies interact frequently, colliding and merging, stripping gas from one another. In voids, those interactions are rare. Galaxies evolve more peacefully, more slowly, following a different evolutionary path. The data also reveals something about the velocities of galaxies around the void. Galaxies on the edges of the void are moving outward, pushed by the underdensity at the center and pulled by the overdensity beyond. These motions are small, only a few hundred kilometers per second, but they are measurable. By tracking these velocities, astronomers can map the gravitational field of the void, revealing how matter is distributed both inside and around it. This velocity data is important because it provides a way to measure the void's expansion. Voids grow over time as the universe expands and as matter flows out of them. By comparing the velocities of galaxies at different distances from the void's center, researchers can estimate how fast it is growing. This growth rate depends on the properties of dark energy, so measuring it provides a way to test theories of cosmic acceleration. The data from gravitational lensing adds another layer. Lensing occurs when the gravitational field of a massive object bends the light from more distant sources. In dense regions like galaxy clusters, this bending is strong, creating dramatic distortions and multiple images of background galaxies. In underdense regions like voids, the lensing signal is weak, but it is still there. By carefully measuring the shapes and positions of background galaxies seen through the void, astronomers can infer how much mass is present. The data shows that the void contains less mass than average, confirming that the underdensity extends to dark matter as well as visible galaxies. This is important because it ties the void directly to the dark matter distribution that shapes the cosmic web. Another fascinating piece of data comes from the cosmic microwave background. This is the faint afterglow of the Big Bang, a sea of photons that have been traveling through space for over 13 billion years. As these photons pass through regions of different density, their energies are affected. Photons passing through voids experience a subtle shift called the integrated Sachs-Wolf effect. Astronomers have looked for this signature in the cosmic microwave background, comparing its temperature fluctuations to the locations of known voids. The data shows a weak but detectable correlation. Voids tend to correspond to slightly cooler regions in the microwave background, consistent with the theoretical prediction. The Bootes void shows this signature as well, adding another piece of evidence that it is real and massive enough to affect light passing through it. The data also includes comparisons with computer simulations. Researchers have run thousands of simulations, modeling how the universe evolves from nearly uniform initial conditions to the complex web of structure we see today. They vary the parameters, the amount of dark matter, the strength of dark energy, the amplitude of initial fluctuations, and see what kinds of voids the simulations produce. The data from these simulations is revealing. They show that voids like the Bootes void can form, but they are rare. In most simulations, the largest voids are smaller, measuring 100 to 200 million light-years across. Voids as large as Bootes appear only occasionally, perhaps once in every few dozen simulations. This rarity matches what we observe. The Bootes void is one of the largest known, but it is not unique. A handful of comparably sized voids have been found in surveys of the universe. The simulations also show how voids evolve. They start as small underdensities in the early universe, regions where matter is slightly less concentrated than average. Over time, gravity amplifies these differences. Matter flows out of the underdense regions toward the overdense ones, and the voids grow larger. The Bootes void likely began as a relatively modest underdensity billions of years ago, and has been growing ever since. Another clue comes from the distribution of voids throughout the universe. If the Bootes void were a complete anomaly, a one-of-a-kind feature, that would be troubling. It would suggest that something very unusual happened in that particular region. But the data shows that large voids are part of a continuum. There are many small voids, fewer medium voids, and only a handful of very large ones. The Bootes void sits at the extreme end of this distribution, but it fits within the pattern. This statistical data is reassuring. It suggests that the void is not a bizarre accident, but an expected, if rare, outcome of the processes that shape the universe. It is like rolling dice. Most of the time, you get ordinary results. Occasionally, you get an extreme result. The Bootes void is one of those extreme results, but it is still part of the same game. The data also includes measurements of the gas inside the void. Even in regions devoid of galaxies, there may be faint wisps of hydrogen gas, too diffuse to form stars but still present. Detecting this gas is difficult because it emits very little light, but observations in radio wavelengths have found hints of it. The data suggests that the void is not completely empty of ordinary matter, just profoundly underdense. All of these clues and fragments, taken together, paint a picture. The Bootes void is a real, massive structure, underdense in both galaxies and dark matter. It formed from initial underdensities in the early universe and has been growing over billions of years. The few galaxies inside it have evolved in isolation, retaining properties that make them different from galaxies in crowded regions. The void affects light passing through it, leaving a subtle signature in the cosmic microwave background, and it fits within the broader pattern of voids throughout the universe, an extreme example but not an inexplicable one. The data does not answer every question. It does not tell us exactly why the initial underdensity was so large, or whether the void will continue to grow forever, or what subtle effects dark energy might have on its evolution. But it provides a foundation, a set of facts upon which theories can be built and tested. In science, data is the bedrock of understanding. Theories come and go, ideas are proposed and discarded, but data remains. The clues and fragments gathered from the Bootes void over decades of observation are the raw material from which knowledge is constructed. And as more data continues to accumulate, our understanding deepens, slowly but surely. The Bootes void has been generous with its data. It has revealed itself to patient observers, offering up its secrets in measured doses. And in return, those observers have pieced together a picture of one of the universe's strangest features. Beneath the surface of the Bootes void lies a deeper mystery, one that goes beyond the mere existence of emptiness. The void is not just a hole in the distribution of galaxies. It is a window into the invisible architecture of the universe, the hidden structures that shape everything we see. To understand this deeper mystery, we need to talk about dark matter. Dark matter is one of the most profound discoveries in modern cosmology, and yet it remains deeply mysterious. We know it exists because we see its effects. Galaxies rotate faster than they should if only visible matter were present. Clusters of galaxies are held together by more mass than we can account for with stars and gas. The cosmic microwave background shows patterns that require dark matter to explain, and the formation of structure, the clumping of matter into galaxies and voids, depends critically on dark matter's gravitational pull. But we do not know what dark matter is. It does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. It is invisible, intangible, detectable only through its gravitational effects, and yet it outweighs ordinary matter by a factor of 5 to 1. Most of the matter in the universe is dark. The Booty's void is intimately connected to this invisible substance. If the void is so underdense in galaxies, it must also be underdense in dark matter. Galaxies form where dark matter is concentrated, where its gravitational pull can gather ordinary matter into dense clouds that collapse into stars. In regions where dark matter is sparse, galaxies simply do not form. So the void is not just empty of galaxies, it is empty of the dark matter scaffolding that would support them. The hidden truth is that the void extends far beyond what we can see. The emptiness we observe in visible light is a reflection of a deeper emptiness in the distribution of dark matter itself. This raises profound questions. Why was dark matter so sparse in this region? What does that tell us about the early universe? About the processes that distributed matter in the first place? To answer these questions, we need to go back to the beginning. In the first moments after the Big Bang, the universe was almost perfectly uniform. Almost, but not quite. Tiny quantum fluctuations, variations in density at the smallest scales, were imprinted on the fabric of space. During the era of cosmic inflation, when the universe expanded faster than the speed of light for a brief instant, these fluctuations were stretched to cosmic scales. The result was a universe with slight variations in density. Some regions were a little denser than average, others were a little less dense. Over billions of years, gravity amplified these differences. Dense regions pulled in more matter, growing denser still. Underdense regions lost matter to their neighbours, growing emptier. Dark matter was crucial to this process. Because it does not interact with light or ordinary matter except through gravity, it could begin clumping together immediately, long before ordinary matter could. Dark matter formed the scaffolding, the invisible framework upon which galaxies would later build. In the region that became the Booty's void, the initial fluctuations must have been such that dark matter was underdense, not completely absent, but sparse enough that gravity could not pull enough matter together to form galaxies. As the universe expanded and evolved, this underdensity grew, amplified by the outward flow of matter toward denser regions. The hidden truth, then, is that the void is a fossil. It is a relic of the initial conditions of the universe, a preserved example of what happens when the quantum dice roll in a particular way. The emptiness we see today is the echo of an underdensity that existed over 13 billion years ago, stretched and amplified by billions of years of cosmic evolution. This realization transforms how we think about the void. It is not just a current feature of the universe. It is a connection to the past, a thread linking the present to the earliest moments after the Big Bang. By studying the void, we are studying those ancient fluctuations, learning about the processes that set the stage for everything that followed. But the mystery goes deeper still. If the void reflects the initial distribution of dark matter, then it also reflects the properties of dark matter itself. Different types of dark matter would produce different patterns of structure. Cold dark matter, particles that move slowly, would clump on small scales, creating a web of fine filaments. Warm dark matter, particles that move faster, would smooth out small-scale structure, creating a web with fewer, larger features. The existence of voids like booties provides a way to test these ideas. If the voids are too large or too numerous, that might suggest dark matter is warmer than we think. If they are too small or too rare, that might suggest cold dark matter with certain properties. By comparing observations to simulations, researchers can constrain the nature of dark matter itself. The void also provides a way to study dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy is thought to be uniform, a constant energy density filling all of space. But what if it varies? What if there are subtle differences in dark energy from one region to another? Voids are sensitive to dark energy because they expand as the universe expands. In fact, they expand faster than the universe as a whole. This is because the underdensity at their centers creates a gravitational push, a repulsive effect that causes matter to flow outward. Dark energy enhances this effect, making voids grow even faster. By measuring how fast the booty's void is expanding, and comparing that to predictions, astronomers can test whether dark energy behaves as expected. If the expansion is faster or slower than predicted, that could indicate something unusual about dark energy in that region. The hidden truth, then, is that the void is not just a hole, it is a probe, a natural laboratory where the effects of dark matter and dark energy are amplified and made visible. It is a place where the invisible becomes detectable, where the hidden architecture of the universe reveals itself through absence rather than presence. There is also a philosophical dimension to this deeper mystery. The void forces us to confront the fact that most of the universe is invisible to us. We live in a cosmos where 85% of the matter is dark, where 70% of the energy is in an even more mysterious form. What we can see, the galaxies and stars and planets, are just the visible peaks of a much larger, hidden structure. The Butes void makes this truth visceral. It is a place where the hidden structure is almost entirely invisible, where the scaffolding is so sparse that even the visible peaks, the galaxies, are missing. It is a reminder that our direct experience of the universe is limited, that we see only a fraction of what is there. And yet, through careful observation and patient study, we can infer what is hidden. We can map the distribution of dark matter by its gravitational effects. We can measure the influence of dark energy by tracking the expansion of voids. We can peer beneath the surface and glimpse the deeper reality. The hidden truth of the Butes void is that it is not an anomaly but a revelation. It shows us that the universe is built on invisible foundations, that the structures we see are shaped by forces and substances we cannot directly detect. It teaches us humility, reminding us that our senses are limited, but it also teaches us hope, showing that through science, through the patient accumulation of evidence and the careful application of reason, we can understand even what we cannot see. The void is a hole in space, yes, but it is also a window into the hidden cosmos, a place where the invisible becomes knowable through its effects. And in that sense, the void is not empty at all. It is full of information, full of clues, full of truths waiting to be uncovered. The deeper mystery is not why the void exists. It is what the void reveals about the nature of reality itself. There are moments in science when a discovery does not just add to our knowledge, but fundamentally changes how we think. The Butez void was such a discovery, not because it broke the laws of physics, but because it forced a paradigm shift in how astronomers understood cosmic structure. Before the void was discovered, the prevailing picture of the universe was one of relative uniformity on large scales. Yes, galaxies clumped into clusters, and those clusters formed superclusters, but the overall impression was of a fairly smooth distribution. The universe was thought to be like a lightly textured fabric, with gentle variations but no dramatic extremes. The Butez void shattered that picture. It showed that the universe was not gently textured but dramatically structured, not smooth but foam-like, with vast voids and dense filaments creating a cosmic web. This was the turning point. The moment when astronomers realized that voids were not minor features, but fundamental components of the universe's architecture. The paradigm shift can be traced through several key realizations. The first was that voids were common. As more surveys mapped the universe, more voids were discovered. The Butez void was one of the largest, but it was not unique. Voids of various sizes were found throughout the cosmos, from modest hollows tens of millions of light years across to giants rivaling Butez. The universe was riddled with them. This discovery changed how astronomers thought about structure formation. Instead of focusing primarily on where galaxies were, they began to focus equally on where galaxies were not. Voids were not just gaps between structures. They were structures in their own right. Anti-structures, perhaps, but no less important for understanding the cosmic web. The second realization was that voids were dynamic. They were not static features frozen in place, but growing, evolving structures. As the universe expanded, voids expanded even faster, their underdensity driving matter outward. Galaxies on the edges of voids were pushed away, while the interiors became increasingly empty. This dynamism meant that voids could be used as tools to study cosmic expansion and dark energy. By measuring how fast voids grow, astronomers could test theories of what drives the universe's accelerated expansion. Voids became laboratories, natural experiments that the universe itself had set up. The third realization was that voids were tracers of the initial conditions. The size and distribution of voids reflected the spectrum of fluctuations in the early universe, the quantum ripples imprinted during inflation. By studying voids statistically, measuring their abundance and properties, astronomers could constrain models of inflation and learn about the universe's first moments. This meant that voids like Butez were not just curiosities but windows into the past. They carried information about the Big Bang itself, encoded in their shapes and distributions. The paradigm shift also involved a change in methodology. Before the discovery of large voids, most astronomical surveys focused on bright objects, stars, galaxies, clusters. These were easy to detect and study, but voids required a different approach. You had to map large volumes of space, measuring redshifts for thousands of galaxies, in order to identify where galaxies were missing. This shift toward large-scale surveys, toward mapping the three-dimensional structure of the universe, became one of the defining features of late 20th century astronomy. Projects like the Sloan Digital Sky Survey, which mapped millions of galaxies, were direct descendants of this paradigm shift. Without the realization that voids mattered, such surveys might not have been prioritized. The turning point also affected theory. Cosmologists had to adjust their models to account for voids. Early simulations had predicted some voids, but not ones as large or numerous as observed. This forced theorists to refine their understanding of dark matter, dark energy, and structure formation. The models became more sophisticated, incorporating better physics and to more realistic initial conditions. The existence of voids also provided a reality check on theories. Any model that could not produce voids like Boote's was incomplete. The void became a benchmark, a standard against which theories were measured. From a philosophical perspective, the paradigm shift involved a change in how we think about emptiness. Before the void, emptiness was seen as merely the absence of things, a background against which objects existed. But the discovery of voids revealed that emptiness itself has structure, that it plays an active role in shaping the universe. Voids are not passive. They push matter away through their underdensity. They grow and evolve. They affect light passing through them. They are as much a part of the cosmic story as galaxies and stars. This realization elevated emptiness from background to foreground, from absence to presence. The turning point also had cultural implications. The Boote's void captured public imagination in a way that many astronomical discoveries do not. The idea of a hole in the universe resonated with people, sparking curiosity and wonder. It became a symbol of the unknown, a reminder that the universe still held surprises. This cultural impact helped drive continued research. Public interest translated into funding for surveys and observations. The void became not just a scientific object but a cultural icon, a piece of the universe that entered popular consciousness. The paradigm shift was not instant. It unfolded over years and decades as more data accumulated and more voids were discovered. But looking back, the discovery of the Boote's void marks a clear turning point. Before it, astronomers saw the universe as mostly full, with galaxies scattered throughout. After it, they saw the universe as a balance between fullness and emptiness, between structure and void. This shift in perspective has proven remarkably fruitful. It has led to new ways of studying dark matter, new tests of dark energy, new insights into the early universe. The void opened doors that might otherwise have remained closed. There is also a lesson here about the nature of scientific progress. Paradigm shifts do not usually come from confirming what we expect. They come from finding what we do not expect, from anomalies that do not fit neatly into existing frameworks. The Boote's void was such an anomaly, and the shift it caused has enriched our understanding immeasurably. The turning point was not just about one void. It was about recognizing that the universe is more complex, more varied, more extreme than we had imagined. It was about accepting that absence can be as informative as presence, that silence can be as eloquent as sound, and perhaps most importantly, it was about humility. The void reminded astronomers that they did not fully understand the cosmos, that nature could still surprise them, that there was always more to learn. That humility is essential to science. It keeps us questioning, keeps us observing, keeps us open to the possibility that the next discovery might change everything we think we know. The Boote's void was a paradigm shift because it changed not just what we know, but how we think. It transformed emptiness from background to subject, from absence to structure. It made voids central to cosmology rather than peripheral. And in doing so, it opened up entire new avenues of research that continue to bear fruit today. The turning point has passed, but its effects remain. The void is now a standard feature of the cosmic landscape, studied and understood in ways that would have been impossible before its discovery. But it has not lost its power to inspire. It remains a reminder that the universe is full of surprises, that even the empty places have stories to tell. Every major discovery sends ripples through the scientific community, immediate consequences that reshape priorities, spark new projects, and redirect careers. The Boote's void was no exception. Its Discovery in 1981 set off a cascade of effects that transformed how astronomers studied the universe. The most immediate consequence was a scramble to confirm and understand the void. Other research teams wanted to verify the finding to make sure it was not an artifact of the survey method or an error in the data. Telescopes were pointed toward booties, redshifts were measured, and the void was studied from every angle. This verification process is a crucial part of science. Extraordinary claims require independent confirmation, and the void certainly qualified as extraordinary. Within a few years, the confirmation was complete. The void was real. Other teams had measured it, mapped it, and found the same striking underdensity. This confirmation had its own consequence: acceptance. The void became an established fact, something that every theory of cosmic structure would have to account for. The next ripple was a wave of new surveys. If one void this large could exist, surely there were others. Astronomers launched ambitious projects to map larger volumes of space, measuring redshifts for tens of thousands of galaxies. These surveys had a simple goal: to chart the three-dimensional structure of the universe and identify all the major voids and filaments. Projects like the CFA Redshift Survey, led by Margaret Geller and John Hutra, began to reveal the cosmic web in unprecedented detail. They found not just voids but walls, vast sheet-like structures of galaxies stretching hundreds of millions of light-years. The most famous was the Great Wall, discovered in 1989, a structure so immense that it rivaled the Bootes void in scale. The void had opened the floodgates. Once astronomers realized that large-scale structure was more dramatic than expected, they poured resources into mapping it. The consequence was a golden age of galaxy surveys that continues to this day. Another immediate consequence was theoretical. Cosmologists had to go back to their models and ask why they had not predicted voids this large. The answer was that the models were incomplete, not fundamentally wrong, but lacking in detail and sophistication. The simulations of the time used simplified assumptions and limited computing power. They could produce voids, but not ones as extreme as Bootes. This realization spurred a wave of improved simulations. Researchers developed better algorithms, used more powerful computers, and incorporated more realistic physics. By the 1990s, simulations were producing voids comparable to Bootes, confirming that such structures were rare but possible within the framework of known physics. The consequence of this theoretical work was a deeper understanding of structure formation. The models became more accurate, better able to reproduce the observed universe. The void had served as a reality check, forcing theorists to refine their work until it matched observation. The void also had consequences for the study of dark matter. If the void was underdense in galaxies, it must also be underdense in dark matter. This meant that the distribution of dark matter was more uneven than some had assumed. The consequence was a renewed focus on how dark matter clumps and spreads, how it shapes the cosmic web, and what its properties might be. Researchers began to study void galaxies specifically to learn about dark matter. These isolated galaxies, undisturbed by neighbours, could reveal subtle details about how dark matter halos form and evolve. The consequence was a new subfield of study, void galaxy astrophysics, which continues to provide valuable insights. Another ripple was felt in the study of dark energy. Although dark energy was not discovered until the late 1990s, the groundwork was being laid. Voids, because they expand faster than the universe as a whole, are sensitive to dark energy's effects. The Bootes void, by existing and being measurable, provided a potential tool for studying whatever was driving cosmic acceleration. When dark energy was finally confirmed, voids like Bootes became even more important. They offered a way to test theories of dark energy, to measure its strength and distribution. The consequence was that voids went from being curiosities to being crucial probes of fundamental physics. The discovery also had consequences for how science is communicated. The Bootes void was one of the first astronomical discoveries to capture broad public attention in the modern era. Its dramatic nature, a hole in the universe, made it easy to explain and intriguing to contemplate. Science journalists wrote about it, documentaries featured it, and it entered popular culture. The consequence was a greater awareness of cosmology among the general public. People who might never have thought about the large-scale structure of the universe found themselves curious about voids and filaments, about dark matter and cosmic evolution. This broader engagement helped sustain funding for astronomy and inspired a generation of students to enter the field. Within the astronomy community, the void had social consequences as well. The team that discovered it, led by Robert Kirshner, gained recognition and respect. Their careful work and willingness to report such an unexpected finding set a standard for observational astronomy. The consequence was that their methods were adopted by others, their approach to mapping the universe becoming a model for future surveys. The void also sparked debate. Some astronomers were quick to embrace the idea of large voids and dramatic cosmic structure. Others were more cautious, wondering whether the void might be explained by less exotic means. These debates were healthy, driving the field forward as different perspectives clashed and synthesized. The immediate consequence of such debates was a flurry of papers, conferences, and discussions. The void became a hot topic, one that every cosmologist had an opinion on. This intellectual ferment was productive, leading to new ideas and insights that might not have emerged in a calmer environment. Another consequence was technological. The need to map large volumes of space and measure thousands of redshifts drove improvements in telescope instruments. Spectrographs became more efficient, capable of measuring multiple galaxies simultaneously. Detectors became more sensitive, able to capture fainter light. The consequence was a technological arms race, with each generation of instruments more powerful than the last. These technological advances had benefits beyond studying voids. They made all of astronomy more capable, enabling discoveries in fields far removed from cosmology. The void had been a catalyst, driving innovation that rippled across the discipline. The Bootes void also had a consequence for international collaboration. Mapping the universe is too large a task for any single team or nation. The surveys that followed the void's discovery often involved collaborations between institutions in different countries, pooling resources and expertise. The consequence was a more interconnected, global astronomy community, one that could tackle problems of unprecedented scale. Finally, there was a psychological consequence. The void reminded astronomers that the universe could still surprise them, that their understanding was incomplete. This was humbling, but also exhilarating. It meant there were still frontiers to explore, still mysteries to solve. The consequence was a renewed sense of purpose, a reminder of why many had entered astronomy in the first place: to explore the unknown. The immediate ripples from the Bootes void's discovery spread far and wide, touching every aspect of cosmology and astronomy. They drove new surveys, improved theories, spurred technological innovation, and captured public imagination. The void was not just a discovery, it was a catalyst, setting in motion a chain of events that transformed the field. These consequences were felt most strongly in the years immediately following 1981, but many continue to resonate today. The surveys launched in response to the void laid the groundwork for modern cosmology. The theoretical work it inspired led to our current understanding of structure formation. The technologies developed to study it are still in use. The Bootes void's immediate consequence was to change everything, and in doing so, it proved that even emptiness can have profound effects, that even absence can reshape the world of ideas. The Bootes void's influence did not end with the immediate ripples that followed its discovery. Its impact has echoed through the decades, shaping the course of cosmology and leaving a lasting mark on how we understand the universe. One of the most profound long-term impacts has been on our conception of cosmic structure. Before the void, the universe was often described in terms of galaxies and clusters, the bright islands of matter scattered through space. After the void, that description became incomplete. Astronomers began to speak of the cosmic web, a term that captures the interconnected nature of filaments, walls, and voids that define the large-scale universe. This shift in language reflects a shift in understanding. The cosmic web is not just a collection of objects, but a unified structure, a pattern that emerges from the interplay of gravity, dark matter, and cosmic expansion. Voids are as essential to this pattern as galaxies. They are the spaces between the threads, the hollows between the knots. Without them, the web would not be a web. The Bootes void helped crystallize this understanding. It showed that emptiness was structural, that the distribution of matter was not random but patterned. This insight has shaped cosmology ever since, influencing everything from how simulations are designed to how observations are interpreted. Another lasting impact has been on dark matter research. The void provided early evidence that dark matter's distribution was highly uneven, concentrated in some regions and sparse in others. This unevenness is crucial for understanding how galaxies form and evolve. Without it, structure would not exist. Over the decades, as dark matter became more central to cosmology, the void remained a key piece of evidence. It demonstrated that whatever dark matter is, it must be able to form the scaffolding for galaxies while also allowing for large, underdense regions. This constraint has guided searches for dark matter candidates and shaped theories about its properties. The void has also had a lasting impact on the study of cosmic expansion and dark energy. When astronomers discovered in the late 1990s that the universe's expansion is accelerating, voids became important tools for understanding why. Because voids expand faster than average regions, they amplify the effects of dark energy, making it easier to detect and measure. Researchers have used observations of voids, including the Bootes void, to test models of dark energy. They measure how fast voids are growing, how matter flows out of them, and how their sizes have changed over cosmic time. These measurements constrain the properties of dark energy, helping to narrow down what it might be. The echo of the Bootes void can be heard in this ongoing research. Every measurement of void expansion builds on the foundation laid by the early studies of Bootes. The void was a pioneer, the first to show how powerful voids could be as cosmological probes. The impact on observational astronomy has been equally profound. The void helped usher in the era of large-scale surveys. After its discovery, it became clear that understanding the universe required mapping it in 3 dimensions, measuring redshifts for millions of galaxies. This realization drove the development of surveys like the 2-degree field galaxy redshift survey and the Sloan Digital Sky Survey, which have mapped hundreds of millions of light-years of space. These surveys have revolutionized cosmology, providing the data needed to test theories and discover new phenomena. They have revealed the cosmic web in exquisite detail, identified thousands of voids, and traced the distribution of dark matter across vast volumes. The Bootes void was the spark that ignited this revolution. The void's impact has also been felt in the development of simulation technology. Modern cosmological simulations can model billions of particles, tracking how matter clumps and flows over billions of years of cosmic history. They can reproduce the cosmic web with remarkable fidelity, including voids like Bootes. These simulations are only possible because of advances in computing power and algorithms. But they were motivated in part by the need to explain observations like the Bootes void. The void was a challenge, a feature that simulations had to be able to reproduce. Meeting that challenge drove the field forward, leading to the sophisticated simulations we have today. On a cultural level, the void has had a lasting impact on how the public thinks about the universe. It remains one of the most recognizable features in cosmology, a concept that even non-scientists can grasp and find intriguing. The idea of a hole in the universe captures the imagination in a way that more abstract concepts often do not. This cultural resonance has helped keep cosmology in the public eye, sustaining interest and support for astronomical research. The void is proof that the universe is not just vast but strange, not just old but structured in unexpected ways. It is a reminder that exploration continues, that there are still frontiers even in the emptiest places. The impact on philosophy has been quieter, but no less significant. The void raises questions about the nature of existence, about whether absence is as real as presence. Philosophers have long grappled with the concept of nothingness, and the void provides a concrete example to contemplate. It is not absolute nothingness, but it is close enough to provoke deep questions. What does it mean for something not to be? Is emptiness a state of being or a lack of state? The void does not answer these questions, but it gives them physical form, grounding them in the actual structure of the universe. The Bootes void has also had a lasting impact on education. It appears in textbooks, lectures, and documentaries as a prime example of cosmic structure. Students learning about the universe encounter the void early, using it as a case study to understand how matter is distributed and how structure forms. Generations of astronomers have been trained with the void as part of their conceptual toolkit. This educational impact ensures that the void's influence will continue. Each new generation learns about it, carries forward the insights it provides, and builds on them. The echo of the void will be heard as long as cosmology is taught and studied. Perhaps the most profound long-term impact is how the void has shaped the questions astronomers ask. Before its discovery, the focus was on where galaxies are. After, the focus expanded to include where they are not, and why. This shift opened up entire new areas of research. Why do voids exist? How do they evolve? What can they tell us about dark matter and dark energy? These questions have driven decades of work and will continue to drive research for decades to come. The void did not just provide answers, it provided better questions. The echoes through time are still reverberating. New observations continue to refine our understanding of the void. New simulations explore its formation and evolution in ever greater detail. New theories propose ways it might constrain fundamental physics. The Bootes void is not a relic of the past, but an active area of research, as relevant today as it was in 1981. The impact of the void is a testament to the power of discovery. 1. Unexpected finding can change the course of an entire field, can open doors that remain open for generations. The Bootes void did that for cosmology. It revealed that the universe was stranger than imagined, and in doing so, it made cosmology richer, deeper, more fascinating. The echoes will continue. Future surveys will map the void in even greater detail. Future telescopes will peer deeper into its interior. Future theories will use it to test new ideas about the cosmos. And future generations will look back at the discovery of the Bootes void as a turning point, a moment when our understanding of the universe shifted and expanded. The void itself remains unchanged, a silent expanse of near emptiness in the constellation Bootes, but its impact reverberates through time, shaping how we think, what we study, and how we understand our place in the cosmos. Behind every great discovery in science, there are people, not abstract minds or disembodied intellects, but human beings with dreams, ambitions, fears, and persistence. The Bootes void was discovered by such people, and understanding their story adds a dimension that numbers and theories cannot capture. Robert Kirshner was the lead astronomer on the team that discovered the void, but he was not working alone. Alongside him were Augustus Oemler, Paul Schechter, and Stephen Scheckman, each bringing their own expertise and perspective. Together, they formed a team united by a common goal: to map the universe and understand its structure. These were not people seeking fame or glory. They were driven by curiosity, by the fundamental human desire to know what is out there. They spent long nights at telescopes, enduring cold, fatigue, and the tedium of repetitive observations. Each galaxy they measured was a small victory, each redshift a data point in a larger picture they were building. Kirshner himself has spoken about the discovery in interviews and writings over the years, and what comes through is a sense of genuine wonder. He and his colleagues were not expecting to find a void. They were simply doing the work, following the data wherever it led. When the void emerged from their observations, it was as much a surprise to them as to anyone. This element of surprise is crucial. Science often advances not through grand plans, but through unexpected discoveries made by people who are paying attention, who are willing to trust their data even when it contradicts expectations. Kirshner and his team had that willingness. They saw something strange in their numbers, and instead of dismissing it, they investigated further. The human element also includes the challenges they faced. Convincing the scientific community that the void was real required not just data but persistence. They had to present their findings clearly, address objections, and withstand skepticism. This is the unglamorous side of science, the part that requires not just brilliance but resilience. The team members were also teachers and mentors. They trained students, passed on their methods, and inspired the next generation of astronomers. Some of those students went on to conduct their own void research, extending the work that Kirshner and his colleagues had begun. In this way, the human impact of the discovery rippled outward, affecting not just the field but the individuals within it. There is also the broader community of astronomers who responded to the discovery. Margaret Geller and John Huchra, who led the CFA Redshift survey, built on the foundation laid by the Bootes void discovery. They expanded the mapping effort, revealing the cosmic web in even greater detail. Their Great Wall discovery in 1989 was a direct descendant of the work inspired by the void. These scientists were dreamers in the truest sense. They dreamed of understanding the universe on its largest scales, of seeing patterns that no one had seen before. They devoted their careers to this dream, often working with limited resources and facing significant technical challenges. The fact that they succeeded is a testament to human ingenuity and determination. The human element also includes those who study void galaxies specifically. These researchers focus on the few dozen galaxies scattered within the Bootes void, treating them as precious laboratories. Each void galaxy is observed, analyzed, and compared to galaxies in denser regions. The goal is to understand how isolation affects galactic evolution. These astronomers spend hours poring over spectra, measuring star formation rates, calculating masses, and mapping gas distributions. It is meticulous work, requiring patience and attention to detail, but it is also deeply rewarding, revealing how galaxies behave when left to evolve in peace. There is a poetic quality to this work. In studying the loneliest galaxies in the universe, these astronomers are themselves engaging in a solitary pursuit, often working late into the night with nothing but their computers and data. The void galaxies become companions, familiar objects that reveal new secrets with each observation. The human element extends beyond professional astronomers. Amateur astronomers, science enthusiasts, and curious members of the public have all engaged with the Bootes void in their own ways. Some have pointed their backyard telescopes toward Bootes, trying to glimpse the emptiness. Others have read about it, wondered about it, used it as a springboard for their own contemplation of the cosmos. In this way, the void has touched lives beyond the scientific community. It has inspired wonder in people who will never conduct research themselves, but who find meaning in knowing that such mysteries exist. This broader human impact is harder to measure, but no less real. The dreamers also include those who use the void in their teaching. Professors incorporate it into lectures, using it to illustrate principles of cosmology and structure formation. Students write papers about it, grapple with the questions it raises, and emerge with a deeper understanding of the universe. The void becomes a pedagogical tool, a way to make abstract concepts concrete. There are also the science communicators, the writers and documentary makers who bring the void to wider audiences. People like Carl Sagan, Neil deGrasse Tyson, and Brian Cox have spoken about cosmic voids, helping the public appreciate their significance. These communicators are dreamers too, dreaming of a world where more people understand and appreciate the universe we inhabit. The human element includes failure as well as success. Not every theory about the void has panned out. Not every observation has been conclusive. There have been false starts, dead ends, and ideas that seemed promising but led nowhere. This is normal in science, part of the process. The dreamers persisted through these setbacks, learning from failure and moving forward. There is also the personal cost. Astronomy is demanding work, requiring travel, long hours, and intense focus. Some of those who have studied the void have sacrificed personal time, family moments, and other opportunities to pursue their research. This sacrifice is rarely acknowledged, but is part of what makes discoveries possible. The dreamers are not superhuman. They are people with strengths and weaknesses, successes and failures, moments of brilliance and moments of doubt. What sets them apart is not innate genius, but persistence, curiosity, and a willingness to devote themselves to understanding something larger than themselves. In telling the story of the Bootes void, we must remember these human beings. They are the ones who turned curiosity into observation, observation into discovery, and discovery into understanding. Without them, the void would still exist, but it would remain unknown, a feature of reality that no one had noticed or appreciated. The human element is also about connection. The scientists who study the void form a community, attending the same conferences, reading each other's papers, building on each other's work. They collaborate, compete, and ultimately push the field forward together. The void has created connections between people who might never have interacted otherwise. There is something deeply moving about this. In studying the loneliest places in the universe, these scientists have built human connections, formed friendships, and created a shared sense of purpose. The void may be empty, but the community studying it is rich with human interaction. The dreamers also include those yet to come. Future astronomers will study the Bootes void with instruments we can barely imagine. They will ask questions we have not thought to ask. They will build on the foundation laid by Kirshner and his colleagues, by Geller and Huckra, by all the researchers who have dedicated themselves to understanding cosmic structure. These future dreamers are children today, looking up at the night, sky, and wondering what is out there. Some will become astronomers, inspired by stories like the Booty's Void. They will carry the work forward, adding their own contributions to the ongoing effort to understand the universe. The human element reminds us that science is not a cold, mechanical process but a deeply human endeavor. It is driven by curiosity, sustained by passion, and advanced by the collective efforts of individuals who care deeply about truth and understanding. The Booty's Void is a scientific discovery, yes, but it is also a human achievement, a testament to what we can accomplish when we dream big and work hard. In the end, the void belongs not just to the cosmos, but to the people who discovered it, studied it, and shared it with the world. They are the dreamers who looked into the darkness and found meaning, who measured absence and found presence, who explored emptiness and found wonder. The human element is what makes the Booty's Void more than just a hole in space. It makes it a story, a journey, a shared human experience. And that, perhaps, is the most profound aspect of all. In science, every major discovery faces opposition. This is not a flaw, but a feature, a crucial part of how science ensures that claims are valid before they are accepted. The Booty's Void was no exception. From the moment its existence was announced, it faced skepticism, questions, and challenges from those who wanted to be certain the discovery was real. The opposition came in several forms. Some questioned the data itself, wondering whether the void was an artifact of observational bias. Others questioned the interpretation, suggesting that the void might not be as empty or as large as claimed. Still others questioned the significance, arguing that the void might not tell us anything new about the universe. Let us examine these challenges and how they were met. The first line of opposition focused on observational bias. Critics pointed out that galaxy surveys are not perfect. They have selection effects, biases that can make certain regions appear emptier than they actually are. For example, if a survey is not sensitive enough to detect faint galaxies, it might miss many objects, creating the false impression of a void. The initial survey that discovered the Booty's Void had a brightness threshold. Only galaxies above a certain luminosity could be detected. What if the void was filled with faint dwarf galaxies that had simply been missed? Kirshner and his team addressed this objection through careful statistical analysis. They calculated how many faint galaxies they might be missing, and showed that even accounting for those, the void was still dramatically underpopulated. They also conducted deeper follow-up observations, searching specifically for faint galaxies within the void. While they found a few, the numbers were still far below what would be expected. This response satisfied most critics. The void was real, not an artifact of the detection threshold. Another line of opposition questioned the boundaries of the void. Where exactly does it begin and end? Critics argued that the void might simply be an irregularly shaped underdense region, not a distinct structure. If its boundaries were ambiguous, how could its size be measured accurately? This was a subtler challenge. Unlike a galaxy or a star, a void does not have a sharp edge. It fades gradually from almost empty at the center to more normally populated at the periphery. Defining where the void ends is somewhat arbitrary, depending on what density threshold you choose. Researchers addressed this by using multiple definitions and showing that regardless of how you draw the boundary, the void is exceptionally large. They also compared it to voids in computer simulations, showing that similar structures appear in models, lending theoretical support to the idea that the void is a coherent feature. A third line of opposition came from those who questioned whether the void was unusual at all. Some argued that given the size of the universe and the number of regions surveyed, finding one very large void was not surprising. It could simply be a statistical fluke, an extreme value that falls within the range of expected outcomes. This argument had some merit. In any large sample, you expect to find outliers. The question was whether the Bootes void was merely an outlier or something that required special explanation. The response to this challenge involved comparing the void to predictions from cosmological models. Researchers ran thousands of simulations, generating virtual universes and measuring the voids they contained. They found that voids as large as Bootes do occur in simulations, but rarely. The void was at the extreme end of the distribution, but not beyond it. It was unusual, but not impossible. This response walked a fine line. The void was rare enough to be interesting, to push the boundaries of what models predicted, but not so rare as to break the models entirely. It was an extreme case, but an expected one. A fourth form of opposition was more philosophical. Some scientists questioned whether studying voids was worth the effort. Voids are, by definition, places where little is happening. Why focus on emptiness when there are so many interesting galaxies, clusters, and active structures to study? This objection reflected a bias toward presence over absence, toward the dramatic over the subtle. But researchers studying the void argued that understanding where galaxies are not is just as important as understanding where they are. The cosmic web is defined by both structure and anti-structure. To understand one, you must understand the other. Over time, this argument won out. As the importance of voids for understanding dark matter, dark energy, and cosmic structure became clear, opposition on these grounds faded. Voids earned their place as legitimate and important objects of study. There was also opposition from those who preferred alternative cosmological models. In the 1980s and 90s, the standard model of cosmology was still being refined. Some researchers favored models without dark matter, or with different expansion histories, or with fundamentally different structures. The Bootes void became a battleground for these competing ideas. Proponents of alternative models tried to use the void as evidence for their theories. They argued that the void's size or properties contradicted the standard model and supported their alternatives. Defenders of the standard model countered by showing that the void was consistent with mainstream cosmology, requiring only minor adjustments rather than wholesale revisions. These battles were fought in journal papers, at conferences, and in private debates. They were often technical, hinging on subtle details of simulations or observations, but they were also important, ensuring that the standard model was tested rigorously before being accepted. In the end, the standard model prevailed, not because it was dogma, but because it explained the data better than the alternatives. The void fit within its framework, adding to the evidence supporting dark matter, cosmic expansion, and structure formation through gravitational collapse. The opposition also came from within the community studying the void. Different researchers had different interpretations of what the void meant, how it formed, and what it could teach us. These internal debates were healthy, driving the field forward as ideas were tested and refined. For example, there was debate over whether the void was a single structure or multiple merged voids. There was debate over the role of dark energy in its expansion. There was debate over whether void galaxies were fundamentally different from other galaxies or simply less evolved. These debates continue today, reflecting the complexity of the void and the difficulty of extracting clear answers from limited data. The battle for truth is not a war with winners and losers. It is a process, a way of ensuring that scientific claims are robust and well supported. The opposition to the Bootes void was not an attack but a test, a way of making sure the discovery was solid before building on it. And the discovery passed that test. The void withstood scrutiny, addressed objections, and earned acceptance. It is now a standard feature of cosmological models. a benchmark for theories, and a subject of ongoing research. The battle for truth also had a human dimension. Researchers on different sides of debates sometimes clashed, their professional disagreements occasionally becoming personal. This is unfortunate, but understandable. Science is done by people, and people have egos, ambitions, and emotions. But ultimately, the process worked. The truth emerged not through consensus or authority, but through evidence. The void was real because the data said so, not because anyone wanted it to be or believed it should be. This is the power of science. It is self-correcting, capable of resolving disputes through observation and experiment. The opposition to the Booty's void, far from hindering progress, actually strengthened it by ensuring that claims were thoroughly tested before being accepted. Today, the opposition has largely quieted. The void is an established fact, and the debates have moved on to more subtle questions about its properties and implications. But the battle for truth was crucial. It made the discovery stronger, the science more robust, and the conclusions more reliable. In a way, the opposition was a gift. It forced researchers to be thorough, to address every objection, to leave no stone unturned. The Booty's void emerged from this crucible not just as a claim but as a solid piece of knowledge, tested and validated by the most rigorous process humanity has devised for determining truth. And that, in the end, is what science is all about. There comes a moment in the evolution of understanding when accumulated knowledge transforms into insight, when pieces that have been gathered separately suddenly click into place, revealing a larger picture. For cosmology, the Booty's void was part of such an awakening, a shift in awareness about the nature of the universe. This awakening was not instant. It unfolded gradually over the decades following the void's discovery. But its effects were profound, changing not just what astronomers knew, but how they thought about the cosmos. The first element of this awakening was the realization that absence is structural. Before the void, emptiness was thought of as simply the lack of things, a background against which objects existed. But the void revealed that emptiness itself has architecture, that it is shaped by the same forces that shape galaxies and clusters. Voids are not random gaps. They are organized features, with boundaries, histories, and dynamics. They grow and evolve. They influence the motion of galaxies around them. They are part of the cosmic web, as integral to its structure as the filaments and walls. This realization changed how astronomers approached their work. They began to study the distribution of emptiness as carefully as the distribution of matter. They mapped voids, measured their properties, and used them to test theories. The awakening was a recognition that to understand the universe, you must understand both what is there and what is not. The second element of the awakening involved dark matter. The void made it impossible to ignore the fact that most of the matter in the universe is invisible. If galaxies trace dark matter, and voids represent regions where dark matter is sparse, then the visible universe is just the tip of an invisible iceberg. This awareness was humbling. It meant that everything we can see, all the stars and galaxies and nebulae, represent only a small fraction of what exists. The bulk of reality is hidden from us, detectable only through its gravitational effects. The awakening brought with it a new appreciation for the role of dark matter in shaping the cosmos. It is not just a correction factor in equations, not just an explanation for rotation curves. It is the scaffolding, the framework upon which the visible universe is built. The Booty's void, with its sparse dark matter halo, made this invisible architecture tangible. The void forced astronomers to think on truly cosmic scales, to grapple with distances and volumes that dwarf everything familiar. 330 million light-years is not just a number. It is a span of space so vast that it challenges comprehension. This awareness of scale brought perspective. Our galaxy, which seems so immense, is a tiny speck compared to the void. Our solar system is invisible on these scales. Earth is less than a grain of sand. The awakening was a recognition of just how small we are, how limited our direct experience is compared to the vastness of what exists. But this awareness was not depressing. It was awe-inspiring. The vastness of the universe, rather than diminishing us, enlarged our sense of wonder. The awakening was a realization that we are part of something unimaginably grand, something that extends far beyond our everyday experience. The fourth element involved time. The void is not just a feature of the present universe. It is a structure with a history, one that extends back billions of years to the early universe. Its emptiness today reflects underdensities that existed when the universe was young, amplified by eons of cosmic evolution. This awareness of deep time added another dimension to understanding. The universe is not static. It is dynamic, evolving, with a past that shaped its present and a future that will shape its form again. The void is a living structure, growing and changing, a testament to the fact that the cosmos is a process, not a fixed state. The awakening also involved a recognition of interconnectedness. The void does not exist in isolation. It is part of the cosmic web, connected to filaments and clusters, influencing and influenced by its surroundings. Matter flows out of the void toward denser regions. Those denser regions exert gravitational pull on the void's edges. Everything is linked. This awareness of interconnectedness challenged the reductionist impulse to study things in isolation. To understand the void, you must understand the filaments around it. To understand those filaments, you must understand the clusters they connect. Everything is part of a larger whole. The awakening brought a new humility to cosmology. It became clear that despite decades of progress, there was still much we did not know. The void raised questions that had no easy answers. Why was the initial underdensity so large? What role does dark energy play in its expansion? Are there subtle variations in fundamental forces that affect its properties? These questions remain open, reminding us that the awakening is not complete. We have gained awareness, but not full understanding. The void continues to challenge us, to push us toward deeper insights. There was also a philosophical dimension to the awakening. The void raised profound questions about the nature of existence. Is absence as real as presence? Does nothingness have properties? The universe seemed to answer yes. The void exists. It has a size, a shape, a history. It affects its surroundings. In some sense, nothingness is as tangible as somethingness. This philosophical awakening extended beyond science. Poets, artists, and thinkers engaged with the concept of the void, using it as a metaphor for emptiness in other contexts. The cosmic void became a symbol, a way of thinking about absence, silence, and the spaces between. The awakening also involved a recognition of our good fortune. We live in a galaxy surrounded by neighbours, in a relatively dense region of the cosmic web. This has allowed us to discover the universe's structure, to see evidence of cosmic history, to develop cosmology as a science. If we lived in the Booty's void, our awareness would be profoundly different, perhaps non-existent. This recognition brought gratitude, a sense that our place in the universe has given us an extraordinary gift, the ability to understand where we are and how we came to be. The awakening was a celebration of that gift, an acknowledgement that awareness itself is precious. The new awareness changed priorities. Astronomers who once focused exclusively on bright, active objects began to appreciate the importance of studying quiet, empty regions. Theorists who once emphasized structure formation began to emphasize void formation as well. The cosmic web became a unified subject of study, not a collection of separate phenomena. This shift in priorities has borne fruit. Studies of voids have provided crucial tests of dark energy, constraints on dark matter, and insights into cosmic history. The awakening to their importance has enriched cosmology immeasurably. The awakening also involved recognizing patterns. The cosmic web is not unique to our universe at this particular moment. It is a natural outcome of the laws of physics, a pattern that would emerge in any universe with gravity, matter, and expansion. The void is part of this universal pattern, a feature that arises not from special circumstances, but from fundamental principles. This recognition brought a deeper understanding of why the universe looks the way it does. It is not accident, but inevitability. Not chaos, but order, emerging from simple rules applied over vast spans of time. The awakening is ongoing. Each new observation, each new simulation, each new theoretical insight adds to our awareness. We see more clearly now than we did in 1981, but we do not yet see everything. The void continues to teach, to reveal, to awaken us to truths we have not yet grasped. In the end, the awakening is about seeing the universe more fully, more honestly, more deeply. It is about recognizing that reality is richer and stranger than we imagined. The Booty's void was one catalyst for this awakening, a hole in the universe that opened our eyes. At the heart of the Booty's void lies a revelation, a truth so fundamental that it reshapes how we understand the universe. This is not just about the void itself, but about what it reveals regarding the nature of reality, the origins of structure, and the deepest principles that govern existence. The revelation begins with quantum mechanics. In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. But even in that primordial state, there were tiny fluctuations, quantum uncertainties in the fabric of space itself. These fluctuations were minuscule, variations in energy and density at scales smaller than atoms. Then came inflation, a period when the universe expanded, faster than light, growing by a factor of at least 10 to the 26th in a fraction of a second. During this exponential expansion, those tiny quantum fluctuations were stretched to cosmic scales. What had been variations smaller than a proton became variations spanning light years, then millions of light years, then hundreds of millions. The revelation is this: the Bootes void, a structure 330 million light-years across, may have begun as a quantum fluctuation smaller than the nucleus of an atom. This is one of the most astonishing connections in all of science. It links the smallest scales to the largest, the quantum realm to the cosmic realm. It shows that the universe carries the imprint of its quantum origins written into its largest structures. The void is, in this sense, a fossil. It preserves information about the quantum state of the universe in its first instant. Every void, every filament, every cluster is a record of those primordial fluctuations, stretched and amplified, but still recognizable. This revelation has profound implications. It means that to understand the largest structures in the universe, we must understand quantum mechanics. It means that the cosmos on the grandest scales is shaped by the same principles that govern atoms and particles. There is a unity to physics, a deep connection between realms that seem utterly different. The revelation also touches on the nature of randomness and determinism. The quantum fluctuations that seeded the void were fundamentally random, governed by the uncertainty principle. No amount of knowledge about the initial state could have predicted exactly where each fluctuation would occur or how large it would be. And yet, from this randomness emerged order. The fluctuations, guided by the deterministic laws of gravity and expansion, grew into the cosmic web. The void is both random in its origin and structured in its evolution, a blend of chance and inevitability. This duality is central to understanding the universe. It is not purely ordered, not purely chaotic. It is an interplay between random initial conditions and deterministic evolution, between the unpredictability of quantum mechanics and the predictability of gravity. The void reveals this duality in concrete form. Its existence required a specific random fluctuation, but its growth and properties follow from universal laws. It is both accident and necessity, both unique and inevitable. Another layer of the revelation involves dark energy. As the void has grown over billions of years, dark energy has played an increasing role in its expansion. Dark energy is thought to be a property of space itself, a constant energy density that does not dilute as the universe expands. In dense regions, gravity dominates, pulling matter together and fighting against the expansion driven by dark energy. But in voids, gravity is weak because there is little matter. Dark energy dominates, causing the void to expand faster than the universe as a whole. The revelation is that voids like Butes are accelerating, growing larger at an ever-increasing rate. They are not static holes but dynamic structures, pushed outward by the mysterious force of dark energy. This makes the void a natural laboratory for studying dark energy. By measuring how fast it grows, how its expansion accelerates, astronomers can constrain the properties of dark energy. The void becomes a cosmic experiment, one that nature has set up for us to observe and learn from. The deepest revelation may be about the nature of space itself. We think of space as empty, as nothingness between objects. But the void suggests that space has properties, that it is not just absence but a dynamic medium. Space expands. It carries energy in the form of dark energy. It is curved by the presence of matter and energy. As general relativity tells us, the void is a region where space is relatively uncluttered, but it is not nothing. It is space itself with all its mysterious properties. This revelation challenges our intuition. Nothingness, it turns out, is not simple. Even the emptiest regions of the universe are filled with space, with quantum fields, with the potential for virtual particles to pop into existence. The void is empty of galaxies, but it is not empty of existence. The revelation also concerns time. The void has a history that stretches back over 13 billion years. The underdensity that would become the Butes void existed when the universe was young, when the first stars were forming, when galaxies were just beginning to coalesce. Over time, that underdensity grew. Matter flowed out of it. Galaxies formed around its edges, and the void deepened. This history is written into the void's current state, encoded in the distribution of the few galaxies within it and the velocities of galaxies around it. By studying the void, we are studying time itself, tracing how the universe has evolved from a nearly uniform state to the complex, structured cosmos we see today. The void is a clock, a marker of cosmic history, a window into deep time. There is also a revelation about unity. The universe seems divided into realms, quantum and cosmic, microscopic and macroscopic, matter and energy, presence and absence. But the void shows that these divisions are artificial. Everything is connected. The quantum fluctuations that seeded the void are linked to its cosmic scale. The dark matter and dark energy that shape it are aspects of a unified reality. The presence of filaments and the absence of galaxies in voids are two sides of the same coin. This unity is beautiful and profound. It suggests that despite the apparent complexity and diversity of the universe, there are underlying principles that connect everything. The void is not separate from the rest of the cosmos. It is part of the whole, shaped by the same forces, governed by the same laws. The revelation also includes our own existence. We are made of matter that was forged in stars, that originated in the Big Bang, that traces back to the same quantum fluctuations that created the void. There is a lineage connecting us to the deepest structures of the universe. This is not just poetic. It is literal. The atoms in our bodies were once part of the primordial soup. They have journeyed through cosmic history, through stars and supernovae, through the formation of galaxies and planets. We are children of the cosmos, and the void is our distant relative, born from the same quantum origins. The deepest revelation of the Booty's void is that it is not really about the void at all. It is about the universe, about existence itself. The void is a lens through which we can see fundamental truths, a window into the deepest principles of reality. It teaches us that the universe began in a quantum state, that randomness and order are intertwined, that space and time are dynamic, that everything is connected. It shows us that even absence is a form of presence, that nothingness has properties, that emptiness is part of the pattern. They are philosophical and even spiritual insights, truths about the nature of being that transcend equations and observations. The void speaks to us not just as scientists, but as conscious beings trying to understand our place in reality. And perhaps that is the ultimate revelation, that we can understand. Despite our smallness, despite the vastness and complexity of the cosmos, we are capable of grasping these truths. We can trace connections from quantum fluctuations to cosmic voids, from the first instant to the present moment, from the smallest scales to the largest. The Boot's void is a testament to human understanding, to our ability to reach beyond ourselves and comprehend something greater. It is a reminder that we are part of the universe trying to understand itself, that consciousness and cosmos are not separate but united. The revelation is complete. The void has spoken, and what it says is this: everything is connected, everything has meaning, everything is part of a larger whole. Even the emptiest places in the universe are full of truth. We have journeyed deep into the Booty's void, explored its discovery, examined its properties, and contemplated its implications. Now it is time to step back, to reflect on what it all means, not just for science, but for us, for our understanding of existence and our place within it. The void invites reflection, because it is, in many ways, a mirror. When we look into its emptiness, we see not just absence, but our own questions, our own struggles to find meaning in a vast and often incomprehensible universe. What does it mean that most of space is empty? This is one of the first questions the void provokes. We live on a planet surrounded by air, immersed in an environment full of things. We are accustomed to density, to presence. The idea that the typical state of the universe is emptiness, that most of space contains almost nothing, is alien to our experience. And yet it is true. The universe is mostly void. Galaxies are rare islands in an ocean of emptiness. Even within galaxies, most of space is empty. The atoms that make up our bodies are mostly empty space. Emptiness is the norm, not the exception. This realization can feel isolating. If the universe is mostly empty, what does that say about our significance? Are we rare flickers of complexity in a cosmos that is fundamentally barren? But there is another way to look at it. The fact that structure exists at all, that galaxies form, that stars shine, that life emerges, is remarkable precisely because emptiness is the default. We are not insignificant. We are improbable, precious, extraordinary events in a universe where most places are silent and dark. The void, then, becomes a backdrop that makes presence more meaningful. Without it, galaxies would not stand out. Without silence, sound has no meaning. Without absence, presence is not appreciable. The void gives context to existence, making the rare all the more wondrous. Another reflection concerns isolation. The galaxies within the Bootes void are profoundly alone. They drift in near solitude, separated from neighbours by distances that are overwhelming even on cosmic scales. If we imagine life existing in one of those galaxies, we can imagine the loneliness such beings might feel, looking out at an almost empty sky. But perhaps loneliness is the wrong word. Perhaps isolation brings clarity. Without the noise and confusion of crowded regions, perhaps void galaxies evolve more peacefully, more true to their nature. Perhaps isolation is not deprivation but freedom. This reflection applies to human experience as well. We sometimes feel isolated, disconnected from others, adrift in emptiness. But isolation can also be a time for growth, for introspection, for discovering who we are when external influences are stripped away. The void reminds us that solitude has value, that emptiness can be a space for becoming. The void also invites reflection on impermanence. It is not static. It grows and evolves. The galaxies within it will eventually die. Their stars will burn out, their gas will be exhausted, and darkness will be complete. On cosmic timescales, even the structures we see as permanent are temporary. This impermanence can be unsettling. It reminds us that nothing lasts forever, that all things pass. But it can also be liberating. If everything is temporary, then the present moment becomes precious. The fact that galaxies shine now, that we exist now, that the universe is structured now, is a gift. One that will not last forever, but is no less real for its transience. The void teaches acceptance of impermanence, of the fact that existence is a process, not a fixed state. This is a lesson that many philosophical and spiritual traditions have taught, and the void gives it cosmic form. Reflecting on the void also means contemplating balance. The universe is not all presence or all absence, all structure or all emptiness. It is both. The cosmic web is a balance between filaments and voids, between density and sparsity. This balance is what makes the universe interesting, complex, capable of producing rich phenomena like galaxies and stars. Too much noise, and we are overwhelmed. Too much silence, and we are isolated. Too much activity, and we burn out. Too much stillness, and we stagnate. The void reminds us that both extremes are part of the pattern, that health and meaning come from finding the right balance between them. Another reflection concerns mystery. Despite decades of study, the void still holds secrets. We do not fully understand why it is so large, exactly how it formed, or what subtle effects it might reveal about dark energy or quantum mechanics. The void remains, in part, mysterious. This is as it should be. Mystery is not a failure of understanding, but an invitation to keep exploring. The fact that the universe still surprises us, still holds unknowns. If we understood everything, there would be nothing left to discover, no wonder left to experience. The void reminds us to embrace mystery, to accept that we will never have all the answers, and to find joy in the questions themselves. There is also a reflection on perspective. From Earth, the void is invisible. We cannot see it with our eyes, or even with most telescopes. It reveals itself only through patient mapping, through careful measurements of redshifts and distances. Our awareness of the void depends on taking a step back, looking at the big picture, seeing patterns that are not visible from a narrow viewpoint. This is a lesson for life. Sometimes we need to step back, to look at our situations from a broader perspective, to see patterns we miss when we are too close. The void teaches the value of perspective, of seeing not just the immediate but the larger context. The void also prompts reflection on connection. Despite its isolation, despite the vast distances involved, the void is connected to everything else. It is part of the cosmic web. Matter flows between it and surrounding regions. It affects and is affected by the expansion of the universe, the properties of dark energy, the distribution of dark matter. Nothing exists in true isolation. Everything is connected, part of a larger whole. This is true for the void, and it is true for us. We are not separate from the universe, but part of it, shaped by the same forces, made of the same material, subject to the same laws. This realization can be comforting. We are not alone. We are part of something vastly larger than ourselves, something that connects us to the farthest reaches of space and time. The void, for all its emptiness, is a thread in the tapestry, and so are we. Finally, reflecting on the void means contemplating, meaning itself. The void has no inherent purpose. It simply is, and yet we find meaning in it. We study it, wonder about it, use it to understand deeper truths. Meaning is something we bring to the universe, not something the universe imposes on us. This is both liberating and challenging. It means we are responsible for creating meaning in our own lives, for finding purpose and value in a cosmos that does not provide them automatically. The void does not tell us what to do or how to live. It simply exists, and we must decide what that existence means to us. In the end, the reflection is this: the Booty's void is a teacher. It teaches us about emptiness and presence, isolation and connection, impermanence and balance, mystery and understanding. It teaches us to embrace perspective, to find meaning in the meaningless, to appreciate the rare and precious in a universe where most places are silent. The void is a space for contemplation, a cosmic koan that invites us to ponder the deepest questions about existence. And in pondering, we find not just answers but better questions, not just knowledge but wisdom. As we come to the end of this journey through the Booty's void, it is time to consider its legacy, what it has given us, and what it will continue to give to future generations. It is also time to return, to come back from the vast emptiness we have explored and find ourselves once again in the familiar, grateful for what we have learned. The legacy of the Booty's void is multifaceted. In science, it has transformed cosmology, shifting focus from individual objects to large-scale structure, from presence to the interplay between presence and absence. It has driven the development of massive galaxy surveys, sophisticated simulations, and new techniques for studying dark matter and dark energy. The void's legacy includes the discoveries it inspired. Without it, the cosmic web might not have been recognized so clearly. The importance of voids as cosmological probes might not have been appreciated. Dark energy studies might have taken a different path. The void opened doors, and through those doors came a flood of new knowledge. But the legacy extends beyond science. The void has entered culture, becoming a symbol of the unknown, of vastness, of the mystery that still exists in our modern world. It has inspired art, literature, and philosophical reflection. It has given people a way to think about emptiness and meaning, about isolation and connection. The void's legacy also includes the human connections it has fostered. Researchers from around the world have collaborated to study it, forming communities and friendships. Students have been trained using it as a teaching tool. Public lectures have brought its wonder to audiences who might never have thought about cosmology otherwise. This human legacy is as important as the scientific one. Science is done by people, and the void has touched many lives, changing careers, sparking interests, and providing a common subject for the community to gather around. The void's legacy will continue into the future. New telescopes, like the James Webb Space Telescope and the Vera Rubin Observatory, will observe it with unprecedented sensitivity. They may discover faint structures within it that current instruments miss. They may reveal details about the few galaxies inside, showing how they formed and evolved in such extreme isolation. Future simulations, running on more powerful computers with more sophisticated physics, will recreate the void with greater fidelity. They may answer lingering questions about its formation, about whether it is a single structure or merged voids, about how dark energy affects its growth. And future theories will use the void to test new ideas. Perhaps it will help reveal the nature of dark matter or constrain the properties of dark energy. Perhaps it will provide clues about quantum gravity or the multiverse. The void's scientific legacy is far from complete. But beyond the specifics, the void's greatest legacy may be simply this. It reminds us that the universe is still full of wonders. In an age when it can feel like everything has been discovered, when maps cover every inch of Earth and space probes visit distant planets, the void stands as a reminder that there are still mysteries, still frontiers, still places that challenge our understanding. This reminder is precious. It keeps curiosity alive. It ensures that future generations will have their own discoveries to make, their own questions to answer, their own sense of wonder to experience. As we return from our journey into the void, we bring back not just knowledge but perspective. We have seen the universe at its most extreme, its most empty, its most silent, and in doing so, we have gained appreciation for what we have. We live in a galaxy rich with stars, surrounded by neighbors we can observe and study. We have a night sky full of light, a cosmos that reveals itself to patient observation. This is not the default state of the universe. It is a gift of location, an accident of where we happen to be. The return also brings gratitude for existence itself. The void shows us how rare structure is, how unlikely complexity is, how precious life is in a universe where most places are barren. We exist against tremendous odds, in a rare pocket of order, in an ocean of emptiness. This gratitude does not diminish us, it elevates us. It makes every moment more meaningful, every connection more valuable, every discovery more wondrous. The void, in its absence, makes presence profound. The return also means integrating what we have learned into how we live. The lessons of the void about balance, about perspective, about embracing mystery, are not just abstract ideas but practical wisdom. We can carry them into our daily lives, using them to navigate our own challenges and questions. We can remember that emptiness is not to be feared but accepted as part of the pattern. We can appreciate the value of stepping back to see the bigger picture. We can embrace the unknown rather than being frustrated by it. The void has taught us, and we can let that teaching shape us. As we close this exploration, we also acknowledge that the story is not finished. The Booty's void remains out there, unchanged by our attention, indifferent to our fascination. It will continue to exist long after we are gone, long after our sun has burned out, long after our galaxy has evolved beyond recognition. This continuity is comforting. The void is larger and more enduring than any individual, any generation, any civilization. It is a permanent feature of the cosmos, at least on timescales that matter to us. It will be there for future astronomers to study, for future generations to wonder at, for future minds to contemplate. We have journeyed into one of the strangest places in the universe and come back enriched. We have looked into emptiness and found meaning. We have contemplated absence and found presence. The Booty's void is a hole in the universe, a vast expanse of near-nothingness 330 million light-years across. It is a fossil of quantum fluctuations, a laboratory for dark energy, a reminder of cosmic randomness and order. It is a teacher, a mirror, a symbol. But most of all, it is a gift of perspective, of wonder, of humility and awe. It shows us that the universe is richer than we imagined, stranger than we expected, more beautiful in its extremes than in its averages. As we leave the void behind and return to our own small corner of the cosmos, we carry its lessons with us. We are part of a universe that contains both abundance and absence, both presence and void. We are threads in a vast tapestry that includes the emptiest places and the brightest clusters. And in knowing this, in understanding our place within it, we find not isolation but connection, not insignificance but meaning, not fear but peace. The Booty's void has given us its secrets, as much as we are ready to receive, and in return we give it our attention, our curiosity, our wonder. The exchange is complete. The journey ends where it began, with the quiet realization that the universe is vast and we are small, but our smallness does not diminish our significance. We are witnesses to cosmic grandeur, explorers of the unknown, seekers of truth in a reality that reveals itself slowly, patiently, to those willing to look. The void is waiting, silent and immense. In the constellation Bootes, it will wait for as long as the universe endures, and we, having visited it in imagination and understanding, return to our lives changed, enriched, grateful. Thank you for joining this journey into the greatest silence humanity has ever discovered. May the vast calm of the Booty's void travel with you into your own stillness tonight, wrapping you gently in the comfort of cosmic perspective, reminding you that even in the emptiest places, there is meaning, there is beauty, there is peace. The void has spoken, and now we rest.